Alright, hell yeah. So we got material mechanics. And heck yeah, we got a problem where we got to do integration because we have some sort of taper. And you know what I mean? The first thing that I do is just make the problem simpler. So we first have to understand what the hell material mechanics is. So material mechanics, I would say the first two rules, just like Fight Club. You know what I mean? One, you can measure, if I have 1 square inch of steel, I can hang 58,000 pounds. Why? Because the strength max of steel is 58,000 pounds per square inch. You know what I mean? And so you could hang a semi just off of this amount of steel. Okay, the other thing is, hey, what if I have a length of steel? You know what I mean? Same 1-inch column of steel, but now how far can I stretch it? You know what I mean? So now we actually, well, I guess I would do a tape measure. Because so the first rule is like, yeah, if we just know what we're dealing with, hey, steel, and it has a strength of this, and it's got an area, you know what I mean, that's much steel, booyah. You know, we take pounds per square inch multiplied by inches squared, and we get pounds, you know what I mean? So that relationship is very intuitive. But then this other one is like, well, if I start hanging, so let's say I have like a 1 meter column of 1-inch steel, and I start hanging a semi, you know what I mean, that weighs 58,000 pounds. Well, this is going to go from 1 meter to a little bit stretched out, you know what I mean, and it's I don't like to use big words, but it's demonstrably visual, you know what I mean. You would be able to see that stretch. And so how much does steel stretch? Well, it's going to be 0.002 times the times the length, and that's going to be how much it stretches. So that's pretty easy. You know, you have this number, and this number is just, you know, and this is another max. It's the strain. You know what I mean? I don't like this. I don't like any of the Greek symbols. But this one's easier to get used to. This is sigma, but this is epsilon, and it's basically saying 0.002. So the max change in length for steel is going to be 0.002. So if I have 1,000 millimeters times 0.002, which is 10 to the 3 times 2 times 10 to the negative 3. Well, hell yeah, these cancel and I get 2 millimeters. You know what I mean? So just there you go. So if we have this bar and it's 1 meter long, and I don't even think it matters if it's tapered. Don't quote me on that, but if we have just a normal 1 meter bar, the max that I can stretch this thing out is going to be 2 millimeters. Cool. And I don't even care if it's, I don't even think it matters if it's like that. Because a thin wire that's 1 meter, it can stretch 2 millimeters. Or the chunkiest, you know, block of steel that's 1 meter can still stretch 2 millimeters. Alright, so that dives into it. So anytime you do material mechanics, because you can get caught up into the equations, you have to go back and be like, well, what were the two fundamentals of material mechanics? It's that we have the strength is equal to force over area, and then we have this epsilon. Epsilon times length is equal to change in length. You know what I mean? But this equation isn't so intuitive just to pop out. I think this one is very intuitive because strength is in PSI, which is in pounds per inches squared. Hell yeah. I multiply by area, bring this upstairs, so we go strength times area, and we get the force. So if this is the max strength of steel, this is the max force. Okay, but now there's another principle. So let's say I still have this 1-inch column. Sure, I can put a load, P, of 58,000 pounds. But that's the limit. Like, I wouldn't want to do that because that's when it's going to, let's say, break. You know what I mean? For all intensive purposes, yes. I mean, we can say that at 58,000 it starts to stretch because we've all seen this graph. Or, you know what I mean, this graph for steel, and then it breaks. But right here is that same, you know, this would be your 58,000 pounds. And at this point, just say, hey, people are going to lose their lives or you're going to lose your job. And it gives us this cool like ceiling that, hey, we have a max, and this is called yield. So it is the yield strength. You might see it like that. This ultimate would be like up here. You know what I mean? That would be your ultimate strength. But the cool thing about maybe this number, you know, for steel, you should just memorize that. But just for the max strength of a material, or the yield strength, let's say. I'm saying max strength is going to be your yield, because you wouldn't want to design anything that gets into the, you know, where you're actually going to change the shape. This is the plastic region. This is where, hey, you know, now your bridge is permanently sagged. But what we do is we design things to stretch out, so it can stretch out 2 millimeters. But the cool thing about this number is the second we, you know, put this semi-truck on the ground, this thing goes back to 1 meter. Like every molecule goes back to the identical spot that it was in. You know what I mean? So that's amazing. So everything stretches out. That's kind of the gist. It stretches out, and as long as you're within this linear range, and that's what we're talking about. Okay. But even that's too much. You might as well just say, oh, this is the breaking point of steel. Don't go higher than that number. Cool. So the first thing that I do is I'll take a problem and be like, well, and this problem, this is tricky because it doesn't have any numbers on it. But let's just say it did. Let's just say this bar was a perfect square, and it, you know, didn't have any taper. And and it's 1 inch, 1 inch by 1 inch, and it's made of steel. So what's P? What's P max? Well, we already said 58,000. And we get that because we take the strength of steel times the area, and that's the force. So we take this equation and just rearrange for the force. And I would kind of write max, so this is your max force. You know, this is the max you can get out of it. But now, and you can do the same thing with this equation. Like, hey, strain, if we already took it to the max force and the max strength, then we can take the max strain, which is 0.002, and that's going to multiply by the length. That's going to be our change in length. Okay, so any material mechanics problems that I do, I just first simplify it, and then two, take everything to the max. Whatever material I'm using, you know, I observe, hey, I know the area, it's 1 by 1 if it's this square bar, and then I see how much force I can get out of it. And then I go back to the problem, and maybe the problem says, hey, we're only putting 20,000 pounds. You're like, okay, you know, I get it. So it's not going to break. So that's a check mark on that, on like, hey, is the strength of the material even strong enough? But then let's go to the change in length, because now you're not using this 0.0. This was only 0.002 if you were using, if you use the max load. Max load is max strength, and that's max stretch, max strain. So this value, this epsilon is called strain, but I definitely like to say stretch or change in length. Even though epsilon is not change in length, it's just associated with change in length. It's like saying, hey, epsilon is proportional to change in length, and it is. All you got to do is multiply by the actual length. Okay, and so, sure, so I can put 2,000 pounds. So I guess let's do that. Let's do that. So if I have this bar, and it's just going to be 1 square inch, but I'm only going to put P of 20,000 pounds. So let's write the equations that we know. So we know that strength, I'm just going to call this strength, even though they call it stress. But yeah, stress is in PSI, but you can also I like to just call it strength. You know what I mean? That might be easier, but it might be confusing, because the first thing I do is say, hey, what's the max strength of the thing? But now we're saying, hey, this isn't maxed out. We're only putting 2,000 PSI, and we have 1 square inch. So, but this equation still applies. So we have force times area, and hell yeah. So we want to know the stress, or you know what I mean? So we throw in 20,000 pounds. Okay, more time on the clock. All right, hell yeah. So we throw in 20,000 pounds and we do 1 square inch. So hell, we get 20,000 psi. So the max strength that steel can take is 58,000 psi. So this is the pressure that's inside every molecule of this, steel bar is only 20,000 psi, and it can take up to 50,000 psi. So that's definitely a fundamental of material mechanics. If you're working with steel, the pressure in between any one molecule can only withstand 58,000 psi. The second that gets more, because you might have a complicated, shape, but if you got a stress right there, if you're calculating that you're 58,000 psi plus, you know what I mean, that part's going to tear apart right there. And the second that part tears apart, that might put 58,000 plus on other sections. So there you go. So that's why we still want to talk in psi, and I just call it strength. Strength is in psi. It's like, hey, train tires, it's not 58,000. Train tires are like 150,000 pounds per square inch. That's the strength max of train steel. You know what I mean? So steel, you can get 3 times as strong as just normal weldable steel that you get at the steel yard. But yeah, I like to say that train tires are pumped up to 150,000 psi. You know what I mean? Because then, yeah, and it definitely applies. Because if your train weighs 150,000 pounds, well, what would that mean? If you put 150,000 pounds on one wheel, each wheel doesn't carry that much, because each wheel will carry the surface area of a dime, which I think is actually relatively small. It might be like less than a quarter inch, you know what I mean? So, but anyway, let's say you did put 150,000 pounds on a train wheel. Well, you would have a flat spot on that train wheel that would have a surface area of 1 inches squared. So it's interesting how you can take something that's steel and be like, oh, it's actually flattening, because you can treat it like it is pumped up to 150,000 psi. Okay, cool. All right, so we did that, so we got that. And then if we only did 20,000 psi, how would we find the change in length? Well, one way is you could be like, well, we have the stress the stress of P divided by stress max, just a proportion. Be like, hey, what's 20,000 pounds divided by 58,000? You know what I mean? So now we have like a linear relationship. 20 divided by 58 is like 0.344. You know what I mean? 34.4% of max. So that's one way to kind of look at it. And if we can calculate our max strain, because we know the strain of steel is 0.002, this is max strain. This is the most you can strain steel, and then let it go where every molecule goes back to the same, where there's no permanent change in length. Okay, so but you could say So you could say that the strain that we want, strain due to P divided by strain max, well, that relationship also is going to be 0.344. It's going to be the same. You know what I mean? So there is a linear. That's why this graph of strain to PSI or stress is linear. So if we go from, so this is 58,000, and we get this for our strain, 0.002. Well, we only went to 20,000, like a third of the way. So we're going to get a third of 0.002 times 0.3. You know what I mean? We're going to get 0.0006. You know what I mean? Probably repeating. All right, so you know what I mean? So you should always have that kind of in the back of your mind. And for the next sheet, we'll actually write the 3 equations. So this was just the introduction to material mechanics. You know what I mean? If you've never seen it, this is the basics to understand what's happening. during a problem. And let's follow this one through. So we wanna find this. So now we take this 0.002, multiply it by the number that we got, times 0.002, and we get 0.006 or 0.00690. Cool. And so there you go. So there's going to be your, no, damn it, add another 0. Sorry, it's going to be smaller. It's so it's 6.9 times 10 to the negative 4, where this was 2 times 10 to the negative 3. So we get a smaller number, smaller strength. And it's a third. This number is about a third, or, you know. So anyway, okay, so now let's say you just had any material mechanics problems and you already knew that intro. The first thing you should do is write the strength equation, is force over area. The next thing you should do is write, I would just write this. Well, this is what I do. I say strength is equal to E. So we have this modulus of elasticity, and again, this is just saying that strength is proportional to strain, and then here's your constant. You know what I mean? So you have a linear relation. So going back to that, you know, graph, we're only in this section of the graph. We're saying that, hey, if this is strain and this, if this is strain and this is stress. That's why I don't like the fact that they're called strain and stress. Like stretch and strength, those are two S words that I think have more, you know, say, hey, this is stretch, this is strength. Cool. But then the linear relationship is that the slope of this line is, you know what I mean, what's rise? So rise over run. So your rise is your strength. Your run is that. So we put this in that order, and we get E. So that's the slope of this line is your elasticity. So it's just the relationship. Now that's a whole tutorial. But what I like to do is I like to write this equation first, this equation second, and let's talk about this, because so we have the strain is 58,000 pounds. Per inch squared, PSI, pounds per inch squared. Strain is 0.002. It's dimensionless. So if this is dimensionless, this has to be in PSI. And for steel, this is 29 million. You're like, holy Toledo. 29 million PSI, pounds per square inch. So if we take a really big number, strain is always a really small number. I mean, that's 2,000. If you had 1 inch of steel and you were trying to stretch it, the max you could stretch it would be 2,000 of an inch. You know what I mean? So you could stretch a 1 inch cube of steel 2,000, which is amazing, the fact that you can even do that. But then when you let go, it'll go back to its original shape. The second you stretch it more than 2,000, it's going to permanently stretch. Anyway, okay, so we have a really big number, and then this is a really tiny number, and then I call this a normal number. So we have a normal number, which is strength, a really small number, which is the stretch or the strain, and then this modulus of elasticity is always a really big number for rigid materials like wood, or wood it's 1 million, steel it's 29 million, concrete, I actually don't know what it is for concrete, but anyway. So, but if you don't know, because the first thing that I do with any material mechanics problems, I know strength because I know this is in PSI, and I know that's pounds per inches squared, and the units are the equation. So we have force over area. Now the next thing, I know that material mechanics I have to use like modulus of elasticity. I need to use this E and this E. So, and then I just know the first thing you should be is, hey, these three are related. So you don't have to memorize this equation, because you can be like, hey, this is a really huge number, this is a really tiny number. The easiest thing is just really big times really tiny is a normal number, kind of a normal number. Or you could do it the opposite. What is a normal number divided by a really small number? All right, more time on the clock. All right, hell yeah. So what is a really, what's a normal number divided by a small number? So if we have a normal number, but we divide it by a really small number, we're going to get a big number. So that means that strength divided by stretch or strain is going to be E, because this is your really big number. And then you can do it the opposite way. You could be like, hey, let's take this normal number and divide it by a really big number, E. Well, what the hell do we get? A normal number divided by a really big number, you must get a small number. So that's going to be your strength. So there you go. So we got this E. So that is true. The initial one that I write, just EE, and I think that might be easier. You know, strength is equal to EE, and then you can figure out the next step from there. And then this one, strength over E is equal to modulus of elasticity. Strength over strain is modulus of elasticity. So there you go. You have three variables, and this is how they are put together. Okay. Now I don't even do that. So I mean, well, what I do is I come in, write the strength equation, force over area, and then write this is equal to E. I know this is just a constant. And then, you know, don't get hung up on modulus of elasticity. It's a fundamental, so if I have steel, this number doesn't change, 29 million PSI. That number is unchanging. Now, like no matter even if it doesn't have a max or a min, this is what it is. You know what I mean? But I could have a strength max of 58,000 PSI for steel, and I could have a strain max of 0.002. So it is good to get into the, I like to write these, max strain, max stretch. Because any problem that you can have a check on reality. You're like, hey, they said this was going to stretch by this amount, and you're like, no, that's way more. Like maybe they wrote the problem wrong. Or you can just have a better understanding by saying you take a problem where they said, oh yeah, this thing is going to stretch this amount, and you found out that the actual strain, actual was 0.0015, and you're like, okay, check on reality. And then you found that the actual stress, PSI of all the molecules, based on what they were saying, actual was 42,000 PSI. Okay, check on reality, because that's under the max stress that you can have. Okay, so this number is unchanging, this number can have a max, and this number can have a max. So the first thing I do is, hell yeah, take things to the max. Obviously, they can have a min. You could just not put any force on it, and then your PSI in the thing is going to be 0 PSI. Your strain in the thing is going to be 0 inches. You know what I mean? It's not going to stretch at all. And so this brings up the next concept, because you'll just get a problem where they say, hey, we're just putting a load on it. But let's say you slowly applied that load. You know what I mean? Let's say you just put, let's say you put 10 pounds on it. You know what I mean? Well, you're going to get a very small change in length. Change in length is going to be very, very small. But let's say you put 58,000 pounds, and you got 1 inch chunk of steel. Well, your change in length is going to be maxed out. You know what I mean? That'll be the max. And so this is a linear relationship from 0 to your max change in length. Just like your PSI in this thing, or your strength, I call it strength, but I guess it's stress. Your stress in your object is going to go from 0 PSI to 58,000 PSI, and because it's a problem, it's probably going to be somewhere on the high end, because you're still trying to get the most strength out of it, but your problem will probably lie right around there. Okay, hell yeah. But now let's get back to these two equations, because this doesn't tell the full picture. You have to write this equation, then this equation, and then I would say, hey, what the hell is strain? Strain, and I just know what strain is. I know it's the change in length divided by the total length. For whatever reason, I can remember that way more than I can. But maybe for you, I've already mentioned how you can take this max strain as 0.002. Well, what the hell would that be? Well, that's if I had 1 meter, you know what I mean? So take your 1 meter. Or 1,000 millimeters, that means I'm going to get I'm going to have to multiply this 1,000 millimeters by my strain, and I'm going to get my change in length, which is going to be 2 millimeters. So just always having a problem, like the simplest problem, that's got to be the simplest. Hey, I know that steel max is 0.002. I'm going to take 1,000 millimeter or 1 meter bar, and it's 1,000 times 0.002. That's 1, 2, 3, 1, 2, 3, and I get 2 millimeters. Sorry, this is millimeters. Okay, and then from this, you can be like, okay, this was the strain, this was the length, and this was my change in length. So there's your equation. So we have strain times length is equal to change in length. And for whatever reason, if I just have to memorize something, I do not memorize this one, I memorize this one. So here's the 3 equations that I memorize. So, and honestly, it's, you know, these 2 I memorize, and then I just know that these 3 variables, 1, 2, and 3, I know that, hey, really big, really small, normal. You know what I mean? So now I've just gotten into the habit of writing it as strength is equal to EE, because that seems halfway intuitive. All right, hell yeah. So now, okay, well, let's get some more light going. All right, hell yeah. Okay, so now we can start this problem. Probably have to take a break for my camera to cool off. Yeah, because we're 30 minutes in and we haven't even started the problem. And we didn't really even do a good job of, so let's write those 3 again. So strength is force over area, strength is equal to EE, and then E is equal to change in length over the total length. So now let's start incorporating these in, because obviously these 2 are equal, so we can go F over A is equal to EE. Cool, but now I know that this E is change in length over L, so I can be like, hey, change in length over L, E. So now these 2 are kind of your bread and butter, and then you won't write it like this, F over A is equal to change in length LE, just because things that you want to find are change in length, and things that you want to find are your force. You want to know how much force you can... so let's grab another sheet of paper and do that one more time. So we're going to write the equation. Strength is force over area. Strength is equal to EE. And I know they call this stress, but, you know, forget that term. You know, it's in PSI. That's all you got to know, is that PSI, strength in PSI. And we already did the train tire analogy. It works. You know, you pump up steel to 150,000 PSI for trains. Anyway, all right, so write that equation, this equation, and then write your strain equation. Change in length over total length. And now put them all together. We do that same thing. F over A is equal to strain. So these 2 are equal. Booyah. And then I can throw this right into there, so I get change in length over length, E. And then, and again, so let's bring it over here, because you're not going to write it like this, because this isn't in its useful form. Now we want to maybe solve for force, so we do that. That's going to be, force is going to be change in length, EA over L. Now, just know that EA always comes in a package. Most textbooks will always write EA in that order, just because EA, they come as a little packet. Okay, now we're going to get an equation just for change in length. L goes upstairs, E goes downstairs. And you get change in length is FL over EA. Now this one you probably want to memorize at some point. Hey, this word spells flee. I don't think I've ever had a mechanics engineering teacher. I've only had one mechanics engineering teacher, but they never mentioned that. But I do. There you go. It spells flee. And then the EA comes as a packet. So, you know what I mean? So those 2 things, you can be like, hey, what was the change in length equation? Well, it's FL over EA. So there you go. So now what this equation can give you is be like, okay, I have a 1-inch bar. And it's 1 meter long. And so I know it's 1 meter, and I'm going to put a force of, let's do that 40,000. You know, 40,000 PSI. And we already did it on that other sheet and found that, well, no, this sheet, what did we do? We did 20,000. So let's do that, 20,000, and we found it was pretty close to that number. So let's do 20,000 PSI. All right, more time on the clock. All right, hell yeah. So we have 20,000 psi. We have a length of 1 meter. We know we're dealing with steel. So this E is just a constant. You know what I mean? It's 29 million. And this number doesn't change. So anytime that they give you E, you should just be like, hell yeah, praise the Lord. You know, you should be excited to see E instead of confused as hell. Like it's the simplest one that just goes into the equation. You know what I mean? E doesn't change at all, so you don't even have to worry about it. You know what I mean? So don't throw shade on this modulus of elasticity just because it's got a funky name, and you really don't understand how it's related because honestly, strength or stress is a bizarre. Strength is force over area, and so that's got two variables that can change, and then strain isn't even change in length. It's change in length over length. You know what I mean? So the slope of this is the rise over run. Strain over E is your modulus of elasticity. But then what? You know what I mean? Modulus of elasticity is 4 terms. And we can solve for it. You know what I mean? So you can also do that, which makes sense. Modulus of elasticity from this picture is going to be F over A, and it's going to be change in length over L. You know what I mean? Because that's what strain is. Strain is change in length over total length. And then if we rearrange this equation for E, hell yeah, you get, well, let's do this one. You know, L goes upstairs, change in length goes downstairs. So you get FL over A change in length. And is that what we got? Hell yeah, FL over A change in length. So there you go. So they're like, no one's ever going to, you know, teach you that, but we just did it in 2 minutes. You know what I mean? And you just get a slowly more intuitive grasp of what the hell modulus of elasticity means. You know, you can play around with it and be like, well, why is glass stretchier than steel? That would be a good one, because glass is stretchier than steel. It just can't stretch very much because the strength of glass is way low. So you ain't stretching glass because it's got a low breaking strength. But steel has a very high breaking strength, and so you can actually visually stretch it. But it is very stiff. Steel is stiffer than glass. And so you can use modulus of elasticity. You know, it's almost modulus of rigidity. You know what I mean? Don't quote me on that. But a high number, you're like, hell yeah. The higher the number, the more rigid. Glass has a modulus of elasticity. Is it the same as wood? Is it 1 million? Don't quote me on that. But anyway, cool. All right, let's move on, and let's do this problem from, you know, using our new equation. So we can say, hey, we want to know that change in length. 20,000 psi, 1 meter. E is 29 million psi, and we're saying this is a 1 inch squared. So let's do it. Change in length is 20,000 pounds per inch squared, and we'll do all the units, you know what I mean, just as. And then length is in meters. E is 29 million. You also might see E 2.9 times, or 10 to the 7, you know what I mean. And did I even get this right? It's 29 million. Yeah, it's 29 million. Okay. But yeah, it'd be 2.9 times 10 to the 7. But 29 million. And that's going to be pounds per inch squared. Hell yeah. And then your A is going to be 1 inch squared because we just chose a 1 inch square chunk of steel. Okay, hell yeah. So, you know, inches cancel. Well, I went too fast. All right, so this inches cancel with... oh, no. These units cancel. Holy hell. Oh, yeah. Sorry. This is not... Why did I choose a 1 meter? That was dumb. And then I'm using 29... oh, my bad. Holy hell. So I just confused units. So we'll have to go back to this one. No, I know. No, we were just fine with this one. Because this one... We were able to swap units because we just found it as a fraction. So we found that the max strength of steel is 58,000 psi, pounds per square inch. And then this is pound. And then we're only putting 20,000 pounds. But we know the max strain is a ratio of 0.002. But this is dimensionless. So you can say, hey, I have 1,000 millimeters. You know what I mean? So 0.002 times 1,000. But for this equation, hell no. You know, our units don't match at all. Meters and inches don't match, so we would have to change meters to inches. So the fastest way to do that is 1 meter is equal to 1,000 millimeters. And then I go 25.4 millimeters, and this is 100% accurate. 25.4 millimeters or 2.54 centimeters is 1 inch. So there you go, 1 inch. Just because in America we just had to throw in the towel and then be like, yep, this is how we're going to make our inches just directly based off of your millimeters, and then we absolutely just chose this. Okay, there you go. So meters cancel, and we're to inches. So now this should give us that same value now. So we got 20,000 times 1,000. What the hell? 20,000 times 1,000 divided by 25.4. I'm going to just store that as x. So we got the top part, and then, oh, no, we just got to divide by 29 million. 1, 2, 3, 1, 2, 3. Okay, and we get a change in length of 0.027. I did something wrong, so that sucks. Oh, yeah, no, duh. This is 0.027 inches, and now we have to actually convert this back. So we got to go 0.027 inches, and then we got to go 1 inch is 25.4 millimeters. So there you go. Multiply this by 25.4. Hell yeah. And we get 0.6896. Doesn't this ring a bell? This is going to be our millimeters of change in length. And unless I... oh, yeah. Over here, I probably made... Oh, no. I was interested in the strain. And yes, the strain was 0.6. The actual strain was 0.0069. But if I take the actual strain here times 1,000 millimeters, I would get 0.69 millimeters of stretch, and I didn't clarify that. That's why these are kind of tricky, where you have strain is change in length over length. You know what I mean? So, like, what are you trying to find? And it might be like, hey, what is the actual strain? Well, the actual strain was a change in length of 0.69 millimeters divided by 1,000 millimeters, where we get 0.0069. And that's in check because this is your max, 0.002, and we got a number that's smaller, and we got a number that's a third of that. So there you go. So even though that was kind of heady and confusing, those are the same kind of confusions you're going to get into where, hey, strain is change in length over length. You know what I mean? So what are you trying to find? Are you trying to find the change in length? That's visually makes sense. But also, you can get the strain. You know, you can get it's kind of like percent change in length. Because if you take change in length over total length times 100%, that's literally the definition of percent change in length. So strain or stretch is very synonymous with percent change in length. But it's just a fractional change in length. You know what I mean? You don't multiply by 100%. But if you do, that kind of makes sense. So if I have 0.002 is the max strain of steel, I can say, hey, multiply by 100%. 0.2%. I can stretch any length of steel 0.2%. And I think just mentally that's going to make a hell of a lot more sense. Whoa, I have 100 inches of, let's say I have 120 inch. I have 10 feet of steel, like steel rod, vertical, 120 inches. Well, I can stretch it 0.2%. Cool. So now what would you multiply? So I go 120 times, do I just multiply by 0.2? No, because I got to get into its fractional form. So I kind of have to divide by 100%, and you get 0.002. So that same number, 120 inches times 0.002. Look at that. This thing can stretch 0.24 inches. It can stretch 1/4 of an inch. So that's another one to throw in your wheelhouse. Hey, if I got 10 feet of steel, a steel rod, and I'm hanging it, and I take it to its max, force, that I can put on it, the max pressure, 58,000 psi, well, it's going to stretch 1/4 inch. So that's hella significant. All right, so hell yeah. I mean, so that's let's not even get to the problem, but spend the full tutorial on being like, well, what the hell is material mechanics at its basics? And why do you actually go get these equations? But once you got this equation, you can rearrange kind of for anything. So that's kind of your gold standard. All right, hell yeah. All right, hell yeah. All right, let's get to it. So this problem, in essence, you know, the second part is just like, hey, let's find the elongation. If we put a P on this, and one, it's got a width here and a width here, and then it's got a thickness T. So if we did a side view of it, it would look like a kind of a top down view. You know, we would have something like that. Oh, and I didn't draw the taper in very well. But it would look like that. You know what I mean? It's not the thickness isn't tapered either. It's not tapered on four sides. It's just tapered like that. So again, you would have two things like there, and then there's the top. That's what the top looks like. All right. So that's kind of a better view of what this thing looks like. So again, you know, we write our equations: force over area, or I mean strength or stress is equal to EE, and then strain or stretch is change in length over total length. Kind of put them together, F over A, and then throw that in, change in length over LE. So then even right here, I can be like, oh yeah, now I got it. I can solve for this. L goes upstairs, E goes downstairs. So change in length is force times length, EA. So hell yeah. So there it is. This would be the answer. You know, they use delta. Delta's change in length is equal to the force. So that's going to be P. I know its length is L. I know the material. Like we said, don't get too confused about modulus of elasticity. It's whatever material you're using, it's got that E. And that does relate. E is what relates, you know, everything in this equation. It is that tie together. Okay, and then your area. But check this out. The area of this, the area right here of that cross section is much smaller than the area right here of this cross section. So now we like, you know, what happens? You know what I mean? So let's just guess. So let's say you didn't know how to do calculus at all. What I would do is just be like, well, let's say this bar was just the thickness, or I mean this width was just B1. Cool. And what would happen there? So if I have a thinner area, if this area, you know, if I have the same force but then on less material, I could pull it farther, right? Because if I have the same force but like a huge chunk of steel, like if I have a steel bar that's this thick and I put like a force on it, I can't move it. But if I have actual just really thin wire, I could probably stretch it out. So having a smaller area is going to get a bigger change in length. And that's basically what this equation says. It's like, hey, if I make this area smaller, any number divided by a smaller number is going to generate a bigger number. So change in length would be bigger in that case, making this one smaller. Now the other thing we could do is just make the length longer. If we have a longer length, you know what I mean, so the length gets bigger, and we don't change anything else. Hell, that's just straight up top, so change in length is going to be bigger. We put more force, bigger force, we're going to have a bigger change in length. Cool. And this E is just going to be constant for whatever material that you're using. But but like I said glass. Well, let's say wood. Wood is a million. So wood is a million. The modulus of elasticity of wood is 1 million. Steel is 29 million. Okay, and if I have the same area, same length, same force on a chunk of steel as I would metal, this number for steel is real big on the bottom, which makes a smaller number all around. So this is going to be a smaller change in length. This number would be smaller on the bottom, generating a bigger number for change in length. So just right there, you have just kind of a general understanding of what's going on with this equation. So the first thing that we could do is be like, hell yeah, I'm just going to say my area is B1, so this is B1 and thickness T. So I'm just going to say area is B1T, and we can find delta is change in length is FL over EA, which is F Well, and then the force is P. So yeah, it's going to be P L divided by E B1T. So that's it. There's my change in length. Done. Okay. Now let's say this whole thing was thick as. You know what I mean? It was just a chunk of steel that was just B2 in height and a thickness T. Well, then I would get force is P, length is L, E is a constant, modulus of elasticity, and then my area, you know what I mean? My surface area is going to be height times width, you know what I mean? So it's going to be B2. Alright, whoops, my camera ran out of juice. But yeah, that area is just going to be the height B2 times the thickness, B2T. So hell yeah. So now this would be the change in length. So this problem, the change in length has to be in between these two. And we know that B1 is a smaller number, so this would be the bigger change in length. And then the B2 is a bigger area and it's divided, so this would be the smaller change. So anyway, so hell yeah. So I know that the change in length is going to be less than PL EB1T, and it's going to be greater than PL EB2T. Like, let's say I didn't study how to do, if I didn't study for the test, but I knew, basics about material mechanics, and if this was on the test, but I'm just like, nah, I got to throw in the towel, and just guess, well, hell yeah, this should get you partial credit. If I was a professor, I would actually give, at least 25%, maybe even 50% for an answer like this. Be like, okay, hell yeah, because it shows your fundamental understanding of making something complex simple. You know that the change's length is going to be in between there. You know what I mean? Just based on that. Okay, but now let's do the problem how it's supposed to be. Alright, hell yeah. So we have material mechanics. We have a problem with a taper. It requires integration. And man, I think I spent like a whole hour just kind of teaching the basics of material mechanics, just to start a problem like this if you didn't know anything from scratch. But we're going to jump right in right here. You need 3 equations for material mechanics. Whoa! All right, the first one, this pen is brand new, Winco. You get 2 pens for 73 cents. That's like 35 cents. It's crazy. It's crazy. But anyway, Winco price is super low. Ooh, it's nice and sharp too. Anyway, so equation number 1 is going to be strength. I call it strength, it's stress. But call it strength. You know what I mean? But strength is force over area. We should all know that. That's the one that's the most intuitive. The second equation relates, this is the scale. You know what I mean? Hell yeah. How many pounds of force can we put over a certain area? Pounds per square inch. The other one is like, hey, measuring. You know what I mean? We can measure something. We can measure a change in length. So even, we're not going to do problem A. That's going to be strain energy. That's where I got into a big hiccup. It's literally the same method to solve the strain energy. But energy is, I need to make a whole other 4-hour video just for me to understand, visually, like what the hell's going on. But we're just going to do, hey, this pen's really slippery. Okay, we're going to do elongation. That's it. Hell yeah, we got the prismatic bar. We're going to throw a load on it. How long is it going to stretch? You know what I mean? And so we, the second equation, strength is epsilon E. EE. If you can remember this, and that's why we did the whole video of like, hell yeah, this should be easy to memorize. And then we know that epsilon is change in length over length. This is strain, just call it stretch. You know what I mean? That's all. Call it stretch, and it just makes so much sense. This thing's going to stretch this much, and then we're going to divide by the change in length. You can multiply by 100%, and then now you have like percent stretch. That's literally exactly what's going on here. They just call it strain, and this is stress, this is strain. I don't like those two names. They're too similar. All right, but now we got our 3 equations, and now you can just kind of plug them into each other. These two are equal, so FA equals EE. Cool. So force divided by area equals epsilon, or strain, times E, the modulus of elasticity. Now this is a constant. I mean, just like, You know what I mean? Just be happy that they give you this number, and then it's a whatever material you're using. This is just a constant. It relates. If you this number actually relates these two. See how like, hey, if I was like, hey, I know strength is over here, and then change stretch is over here. Hey, it would be cool if these were proportional, and you know, with math equations, proportionality. You probably have a constant. There's no way you're not going to have a constant, depending on what units you use. This is in PSI, and then this is going to be unitless. You know what I mean? So hell yeah, this K has to be 1 over PSI. So booyah, booyah, and then you get this equation. So E is a constant. Now let's get on with it. And then so we get these two are equal. Now we can throw this into strain. So we got force over area is equal to change in length over length times modulus of elasticity. Now this isn't the friendliest, you know what I mean? Looking at this isn't the friendliest because it's not very useful. But this is what, hell, let's solve for change in length. That's what we're trying to solve for. L goes upstairs, E goes downstairs. So now we have change in length is force times length. And then you always see this as EA. It comes as a little package. E is a constant. A is going to be whatever areas you're going to work with. So more on that in a second. But there you go. You got change in length is FLEA. Cool. It spells the word flee. I don't know if that's useful. But obviously the EA is downstairs. Okay. All right. So hell yeah. So this is the equation. So why can't we just get it done? Well, let's try it. Change in length. Our force is P. Our length is L, and then our E is a constant, like I said, and then our A. Well, what's our cross-sectional area? Well, let's take a little look at this. So, like from a 3D perspective, this looks like this. You know what I mean? It's not tapered. It's not tapered in 4 directions. It's just tapered in these 2 lines. Okay, so the cross-sectional area right here, that should be pretty easy. And then this thickness is T. So the cross-sectional area is, well, B1, the height, B1 times T. Okay, the cross-sectional area over here is B2 times T. Okay, so we have 2 different cross-sectional areas. So which one do we actually put in for this? You know what I mean? If you didn't know calculus, and you just wanted a just guess approach, well, throw in this one. Pretend like this bar is just really narrow. And, you know, mentally, we kind of know what these equations do. So we can say, hey, if I have like a thin piece of wire and I put a load on it, it's going to stretch, like maybe visually. But then let's say I have a thick piece of steel and I put that same load on it, it's not going to stretch as much. So now you see that this area downstairs, if area is a small number, like I said, the thin wire would have a tiny cross-sectional area and maybe the same length. And then we put the same P on it, it's going to stretch quite a bit, maybe even visually, you know what I mean? But then if this area gets real big, we're dividing by a big number, so hell yeah, this becomes real small, change in length becomes real small. Okay, so now we know that, hey, if we just design this, if this is our cross-sectional area the entire way, the smaller one is going to stretch a bit, so we're going to do that one. So basically, change in length would be PL E. Now the area for this small cross-sectional area would be the thickness times the height, B1. So there you go. And let's say for all intensive purposes, thickness is 1 inch, B2 is 2 inches, and then B1 is 1 inch. You know, just throw some simple values in there, and you can see that this will be PL ET. That's it. You know what I mean? Because we got the number 1 right there. Okay, now let's say, hey, let's just make this thing a constant thickness B2, 2 inches. You know what I mean? So now we have 2 inch width, thickness of 1 inch. So now our change in length is our load times our length divided by E. The cross-sectional area would then be T B2. Cool. And if we said B2 is 2 inches, now we got PL. This is 2. I'm just going to bring the 2 out front. You know, always brings your kind of numbers and constants in front of your variables. So then we have ET. So there you go. So now this change in length will be half. See how this is the same thing, but this one is like kind of like a ratio of 1/1, and this one is a ratio of a half. So there you go. So if we do make it hella thick, it's only going to stretch a half. If we make it thin as this cross-sectional area, it's going to stretch like a full 1 unit. Okay, so now can't we just say this problem is going to, be right in between? That's a 100% yes sir. Check the box. You know what I mean? Because right now you just solve the problem, and you'll see why in a second. So the area, see how the area is downstairs, and we had this 2 here and the 1 there. Sure, you know what I mean. Let's just find this. So this is 1 and this is 0.5. What is the halfway between 1 and 0.5? 0.75. And then the fraction, well, let's do this. How you would find the middle point of anything is take this number, let's take 1 plus a half divided by 2. So let's do that. So you would change this into a 2/2 plus 1/2. You know what I mean? Use your math skills, because now this upstairs and divide by 2. This upstairs is going to be just 3/2, and now you're going to divide by 2. Always change the downstairs into a fraction, even if it's a whole number, because now dividing by 2/1 is the same thing as multiplying by 1/2. Cool. And now you'll get the fraction 3/4. Cool. So now we know that 3/4 is right in between, and that's literally that really just answers the problem right there. So you could say, and this gives you no value. So if you just want, hey, what's the formula for change in length? I'm going to be 3/4. Ah, damn it! More time on the clock. All right, hell yeah. So the answer to this problem is going to be 3/4 PL over E. Now what do we do for A? You know what I mean? Oh, that is a conundrum. Do we just say whatever this area is? Is that where we got the thickness? Yeah. So if it was just, just imagine it's hella thick. No, it's you would have to. Oh, so that was bizarre. Because what's the actual? I think this method is off B1. You know what I mean? It's off of 1 inch, and that makes sense. I think probably not, but yeah. So then this would be B1T. So that's your answer at the end of the day. Whatever your smallest cross-sectional area is, it's going to be 3/4 that. That might not be true at all. Oh, no. It's, oh, hell. I think this method said well, let's try it one more time just to make sure. So our P is equal to PL over E, but we do not know what our area is. But for our area, we can do something. Holy Toledo. Our area is either going to be 2. No, that's not going to work. I need to rethink this. Just a second. Alright, hell yeah. No, this is good. This is why I make these videos, because I come up with little topics in my head that I'm just like, okay, this explained it. But it only explained it if this was 2 and this was 1. And then we said, well, in this case, no, and then we chose the halfway point. So we wanted to find a way to be like, well, that is a really good way to do it. Just like whatever this area was the biggest area, find the change in length if it was the biggest area for the biggest A. You know what I mean? And then find the change in length for the smallest A. And we did that. And then with our setup, we said, hey, let's say this is 2 and this is 1. Sure. So we get a number like this, with the area twice as big, we get half the change in length. And with the area half as big, we get just kind of a full change in length. So halfway between 1 and a half is 3/4. So for this scenario, you're going the change in length is going to be, let's say the area was just this fat area. It's not going to, or no. For this scenario, it's going to be if this was the narrowest. If this was just made with the narrowest area, a slender bar, no taper, with the narrowest area, it would just be, we're going to expect a lot of change in length, and then make it 3/4, and that's going to be very close to the actual change in length for this. But you could have a scenario where this is, let's just say this is 1 inch, and then this over here is just 0.9 inches. You know what I mean? So it's basically not tapered at all. So then this one's going to be PL over ET1, and then this one, that's going to change the length for this one, and then this one's going to be PL ET.9. You know what I mean? So 1 divided by 0.9, this is going to have a change in length of 1.11, and this is going to have a change in length of 1. You know what I mean? So what's halfway between these? You'd go 1 plus 1.1 repeated divided by 2. So let's do that. Plus 1 divided by 2, and you get our answer of 0.05 repeat. You know what I mean? So, and that's going to be a very good guess for the change in length of this scenario. So let's do one more scenario where, hey, this is going to be, let's go back to our 2 inches over here. And then we're going to taper it to nothing. So now, if we take the change in length of this, well, change in length is PL over E, but the area is 0. So you'd have to divide by 0 here. So this would be an infinite change in length. Change in length is infinite. And then you'd have change in length over here. Change in length is PL E, and I guess there's a T here, T times 2. So this change in length would be, you know, a ratio of a half and infinity. What's the halfway point? Well, that's nonsensical. So you could just say, well, that's nonsensical. Let's just take the change in length here, and then your you know what I mean? This would be 1, and anyway, holy hell. So that one actually, well, I didn't realize that was going to be an infinity. So that one's not going to be, that's not going to be visually friendly. But the same thing, you could be like, hey, well, let's just say the whole bar is just 1 inch. You know what I mean? And maybe that is similar. Yep. And let's do that same scenario where if we do have this be 2 inches and this is 1 inch, you know, it's very simple to be like, hell, I can just make a 2-inch bar and then or a 1-inch bar, but let's make a bar halfway in between, because wouldn't halfway be in between also be you know, correct? So we would have if this is 1. Then you're going to have like there to there, so you're going to add a 1/4 inch. So you have 1, quarter, yeah, so it's going to be 1.5. So we'd have a bar that's 1.5. So let's do that. Change in length is PL divided by ET 1.5. All right, hell yeah. So what's 1 divided by 1.5? 1 divided by 1.5? Well, that's 0.66. You know, repeat. So hell yeah. So now besides this one, I can't have a good guess for this one. But what we did is we took the halfway point. That seemed right. So already we used 3 guessing techniques. The 3 guessing techniques were make it, and we chose our B's up front. You know what I mean? And made sure this wasn't 0. That seemed a little bit nonsensical. But we just made this one twice that one. And that's a common scenario. That seems like a common taper that you might do. And so from that one setup, you know what I mean, we found that the change in length was either 3/4 PLET, you know, times a ratio of 1, or from the halfway point, we found that the change in length was 0.66 repeat PLET, you know, with a ratio of 1 down there. All right, hell yeah. Oh man. Oh, okay, yeah. It's not technically a ratio of 1. This is still, change in length is PLET, but then the height, you know what I mean, thickness times height, and the height is 1.5. But that just gets a ratio of 0.6. You know what I mean? If you're comparing, you know, change in lengths based on areas or ratios of areas, then there you go. Because we're saying, hey, we're going to choose B2 as 2, B1 as 1, and then we're going to kind of split those in the middle. So still, this is a good representation of a ratio between B2 and B1. All right, hell yeah. And in general, you're going to get a problem that says, hey, we know the thickness over here, the height, and then we know the height over here, it has a taper. And so we would use those 3 scenarios to try to find an average. You know what I mean? So we did. We actually found 0.75 and 0.66. So now we could, you know, we found 2 guesses. We could just take the midpoint between those. So we go 0.75 plus 0.66. So let's do that. We got this 0.6 plus points. And then you divide by 2. And that's going to be the average between those. Hell yeah. This is such a good equation to know. It's like, hey, if I want to find the average between 2 numbers, we'll just add them together, divide by 2. And then you get 0.708, which is literally, for this scenario, this is going to be probably 100% accurate. I mean, actually, it just stumbles across it. This was a really good guess for the actual change in length for a bar that's 2 inches over here and 1 inch over there, or where B2 is twice B1, where we got B2 is B1 times 2. Okay, hell yeah. But what for this problem, and if we want to find the elongation of the bar, we need to have a formula that we can throw in any B2 and B1. So even in this situation, we could throw in that B1 is 0, and it would still give us a change in length. But like I said, for this one, well, let's just guess. If this was 2 over here, and it tapered to nothing, like what is our guess? Well, using this method, we would say, hey, like this, we're going to draw a line halfway, and we're going to say, let's say we do the bar right here, and then we do the bar right there. So this would be 1 inch. So we're going to say if we have a 2 inch to 0 taper, it's going to be the same thing as our B2 equals B1 equals 1 inch. So then our change in length would be PL divided by ET times that height, which would be 1 inch. So T, like the area is the thickness times the height. So we're saying, hell yeah, this is the height, and then that's the thickness. Thickness, we're just going to choose a 1 inch. But booyah, we would get that, and we would get PL over ET. Hell yeah, more time. All right, hell yeah. So we used our guess and check method, and we're going to do one more because we're going to have to integrate this thing. And well, let's talk about how this equation works. So let's say we have a bar, and then we throw up a force on it. You know what I mean? It's going to change in length, and it's not going to be much, especially if it's steel. 1 meter of steel, that would be 1,000 millimeters. We've already said that the max strain, the max change in length per total length is going to be 0.002. So you take this number times the length, So 0.002 times 1,000 millimeters, and you get a 2 millimeter change in length. That's the most you can stretch steel so it doesn't, one, break or fail or kill people, lose your job, or also, but you keep it within this elastic range where the second you let go, you can stretch it to 2 millimeters and then let go, and every atom will go back, every molecule of steel will go back to its original length and shape. Okay, hell yeah. All right, so we have this property. What the hell was I getting at? Oh, yeah. But we have a tapered bar. So we want to figure out, well, how to... Oh, okay. So check this out. So a 1 meter bar can stretch 2 millimeters. So let's say we have a half meter bar. How much can that stretch? Well, 1 millimeter. You know, and then we have 2 half meter bars. So we could cut this 1 meter bar into 2 half meter bars, and we could stretch these 1 millimeter, both of them. And let's say we only had a 1/4 inch bar, you know what I mean? And we had 4 of them. Now we could stretch these 1/2 millimeter each. And then if we had an 1/8, you know what I mean? I don't want to draw all 8 of these, but 1, 2, I probably missed one. But anyway, and then now we have 0.25 millimeters. So each of these bars, this would be 500 millimeter. So the length on this is 500 millimeters or 1/2 meter. Length on this is 250 millimeters, and then we'd have 125. So in 125 millimeters is about 5 inches. So we would have a 5-inch bar, and we could stretch it 1/4 millimeter. Hell, you might be able to see that. So even with like a 5-inch bolt, if you had a 5-inch bolt, you could stretch it 1/4 millimeter. You know what I mean? You might be able to register that on like they do make digital calipers that are pretty accurate. But you might be able to register that, and then it'll go back to its original shape. But anyway, what we're saying here is that each of these sections can only stretch so far. So we have this equation that says change in length is PL over EA. And we can say that this is the same thing as PL divided by 2 over EA plus PL divided by 2 over EA. You know what I mean? Let's say we just have a uniform thickness bar. That's basically saying the change in length of this section plus the change in length of this section is going to just equal, you know what I mean, the total length. And if it's uniform, hell yeah. Our E is a constant. Our A is going to be like 1 inch cubed if it's a 1 square inch bar. You know what I mean? And then the load's going to be the same. And doing a free body diagram, if you have a bar and you put a load this way and you're just up against something, up against a wall, load P, every little section, you could cut any section away from this, and basically you'll get an equal and opposite load. And we've done that where it's just like, hey, this thing's not traveling through space. F equals ma. If you do identify a force, you should observe acceleration, but we see an equal and opposite force holding this thing stationary. It ain't moving. It's because you have equal and opposite. But we can take any slice out of this bar and say, hey, there's still the same force on each of these slices. So you could take a 1/10, you know what I mean, or a 1/100th inch slice and say the change in length of that 100-inch slice is going to be P, and then it's going to be L divided by 100 divided by EA. And you could sum all those together, PL divided by 100, but as long as the as long as the area doesn't change, once you summed all those together, you're still just going to get PL over EA, you know what I mean? And we're done. But in our case, our areas do change. So this just shows that, hey, we will still use the guessing game, but we'll say, hey, let's say this area is going to be, so we're going to take the halfway point. Let's say for half of it, it's just B over 2, and the other half is going to be B1. Well, now we're just in, because now we can say, hey, the change in length total is going to be PL divided by 2, so half the length, divided by, for this, is going to be E. The area is thickness times height, So there you go. And now we're going to take P L divided by 2 for over here. This is going to be E thickness times B1. And hell yeah. And it still works with our scenario. So the 2 comes downstairs. You can kind of see that. And then let's say B2 was 2 inches and B1 was 1 inch. So now you have, so in this scenario, this goes to 2 inches. So now you have like a 1/4 ratio plus, and this goes to 1 inch, plus a 1/2 ratio. So in this scenario, yeah, and this is the number. This is the, it might look weird just because we did it, like this is actually computing the change in length. The other one we kind of just said, hey, let's pick the bigger number and then a smaller number, and then we're just going to find the midpoint. But here is actually fine. So we got 0.25 plus 0.5. That's going to be 0.75. So we already check box. Like this scenario is the same thing as saying, hey, let's take the change in length of the bigger one, which is small, and then the change in length of the smaller one, which is going to be larger, and then find that midpoint. But this just actually gives you a value, and so this was a pretty good guess. So now we're going to go over that guess and check method, and I got to throw some more time on the clock. All right, hell yeah. So we just took that taper and said, hey, the halfway point was B2, and then we went B1. So B2 and then B1. Now, the simplest thing to do is to cut this thing into 3 sections, and you'll see why in a second. Because if this is 2 inches and this is 1 inch, well, what's halfway between 2 and 1? We're going to say that this is 1.5. So that is going to make more sense than divvying this thing up into 4 sections. 4 sections will just be a mathematical nightmare, because then you'll have to kind of, this might be like 1.7, 1.66 maybe, and this might be like 1.3, you know what I mean? It's just, it doesn't work as nice. So now let's do this scenario. Our height is going to be 1 inch, 1.5, and 2. Our length is going to be the total length divided by 3. So we got 1/3 of the length. So let's do this. So change in length total will be the first one. And then our equation that we're using is FL over EA, just to throw it out there. So for the first one, we're going to get P. Our length is L over 3. And then our E is constant. That doesn't change. But our area for the first one is going to be thickness times the height, which is 2. So there you go. That's going to be the first one. Second one, P L over 3 ET times the height, 1.5. Cool. Next one is going to be P L over 3 ET and then 1. So already you can see that, hey, these numbers won't change. E is a constant. That's the material modulus of elasticity. Kind of the higher the number, the stiffer the material. Cool. And then P is load and force, pounds or newtons or whatever. Thickness, that's what we got there. So those don't change. So we can kind of just, divide those out. And then L, the total length won't change. So now we have this scenario. We have 1/3 divided by 2 plus 1/3 divided by 1.5 plus 1/3 divided by 1. And 1.5, that's going to be 3 halves. So we could already do that 3 halves. So then so if you're doing mental math in your head, just always take the thing downstairs and divide it by 1, because because then you can flip even 1 divided by 1. Well, that's just going to be switch it around. So instead of 1 divided by 1, it's going to be, we'll flip it around. It's going to be 1 divided by 1. Cool. That's going to be 1/3. All right, so hell yeah. So this is going to be divide by 2 divided by 1. That's the same thing as multiplying by 1 divided by 2. Cool. 3 divided by 2, same thing as multiplying by 2 divided by 3. So this is going to be 2/9. So hell yeah. So now we have, we don't have to get too confused, but 1/6 plus 2/9 plus 1/3. And then whatever this number is, I don't think I could do this one. This is 0.333. So guess what? Guess what's half of 30? Well, that's 15. But it's actually 0.666. So there you go, 0.166. and then 2 ninths. I don't even know what a ninth is. I think it's 0.11. So hell yeah, it's 0.22. So don't you just like doing this mental math in your head? And then you can be like, hell yeah, 0.3356. So I know it's going to be at least 0.6. But then we have 6, 7, 8, 9, 10, 11. So another 1 plus 1. So maybe it's 0.71 repeated. You know, that might be a really good guess just for mental math. Well, let's throw it in. And I got to double check this, because this is going to be 1 divided by... and the other thing is just, hell yeah, if you can see, this is 1/3 out, and then you have way simpler. This is going to be 1 over 2 plus 1 over 1.5 plus 1 over 1. Essentially, I should have just went to there. But you have this 3-bar setup. This is your fraction. So let's do that. So this is going to be 1 divided by 2 plus 1 divided by 1.5 plus 1. And that's going to be 2.16 repeated, divided by 3, and we would get our number 0.722 repeat. Hey, so we were pretty close on our mental math. Let's see if this matches up. So 1 divided by 6 plus 2 divided by 9 plus 1 divided by 3. Hell yeah, same number. It's always good to work on your mental math skills, especially with fractions. And booyah, so now we're getting really close to the actual answer. So there you go. And we'll do it maybe 1, even 2 more times since we're on a roll. So now we're going to divvy that 3 up into 5. And you'll see why in a second. So we got 1, 2, 3, 4, 5. Now all these are the same length. I just didn't draw them to scale. This is going to be 2. So we got 2. This is going to be 1.5. This is going to be 1. So halfway between 2 and this is going to be 1.75. This is going to be 1.25. See, that's why doing it into 3s, 5s, and then the next jump would be 7. You know what I mean? Or I think, unless you would do 1 there, 1 there, 1. So we did 3 chunks, and then we added 2 more chunks in between and got 5. So then once we get 5, we would add 1, 2, 3, 4 chunks in between, and we go from 5, 6, 7, 8, 9. We go to 9. So hell yeah, you go to 3 to 5 to 9, and what is that, Fibonacci? But anyway, all right, let's do it. So now our length though is 1/5. So now we can go change in length, PL over EA. That's going to be, so the P L comes out, PL comes out, and we do have this 1/5, and then our area is going to be 1 divided by 2 plus 1 divided by 1.75 plus 1 divided by 1.5 plus 1 divided by 1.25 plus 1 divided by 1. So let's do this in our calculator, and this will probably be the last time. So we're going to do 0.5 plus 1 divided by 1.75 plus 1 divided by 1.5 plus 1 divided by 1.25 plus 1. Divide by 5, hell yeah. And we get 0.707619. Well, it isn't, what's cosine 45? So that's really close to the cosine 45. I don't know if that's actually going to be the same as that, but we're approaching this number, you know what I mean? So 0.70 something, and you can see that it's decreasing. So yeah, so 0.7 is a really good guess of the elongation of this bar, given that B2 is twice B1. You know what I mean? For just this one scenario. Like if it actually gave us this scenario. But what we have to do is be like, hey, given any B2 and B1. You know what I mean? B2 can be, so you can either have like a bar that's hardly not tapered at all, or you can have a bar, or a bar that looks like that, where B1 is equal to 0. And this bar is where B1 is equal to B2. You know what I mean? So those are, we need to get an equation for every scenario. So that's what we're going to do next. And we need calculus. So what I just showed you was a scenario where we chose the ratio between B2 and B1. But we didn't. I mean, well, let's use this because I'm still fascinated. I mean, this is like, well, if you didn't have calculus, but you still wanted to come up with a equation like this, where you could throw in any B1 and B2, out to like, 5 segments, that would be fascinating. So we're gonna spend our time doing that. So we're gonna take the first setup, and we're gonna split it in half. So we're gonna say, hey, this is B2, this is B1, and we're gonna say change in length is going to be FLEA, and that's going to be FLETB2. Length is divided by 2, plus F length divided by 2 ETB1. So that's that scenario. Okay, let's do the third scenario, where this is B1, this is B2, but this is going to be B1 plus B2 divided by 2. Remember that midpoint rule? Hell yeah. So now we're going to get change in length is, and I guess F is P, so we have a load P. So we're going to say P, L divided by 3, E, T, and then we're going to say B2 plus P, L divided by 3, ET, B1 plus B2 divided by 2, plus PL over 3, ET, and then B1. Hell yeah. So there you go. We'll simplify it. We're going to throw some more time on the clock. All right, booyah, booyah. So even just this right here, we can factor out a 2. So that can bring the 2 upstairs. You know what I mean? The 3 goes downstairs. So there you go. And but in essence, we can factor out L over 3, or we have the P, E, T, and then L. We can factor out the 1/3. Now what we're left with is 1 over B2 plus 2 over B1 plus B2. So there you go. Plus 1 over B1. So there's a nice series formula for this. So you can now throw in any B1 and B2. And let's do that. Remember how we got, like, if we said B1 was 0, we were going to get, and we made an area of 0. You would get an infinite change in length. But now, let's say B2 is 2, and then B1 is 0, and let's find that out. Because we thought it was going to be very close to PLET, just thickness of 1. So we're going to see if that jives. So let's do it. You're going to get change in length, PLET, 1/3. This is going to be 1/2 plus 2 divided by, well, this is 0, so it would be just 2 divided by 2 plus, this is 0. So hell yeah. So now you get 2 plus, so you're going to get 2.5 here, and half of 2.5. Well, this is very close to 3. 3 divided by 3, that's really close to that one, the guess that we guessed. But we're going to get 2.5 divided by 3. So it's a little bit smaller of a number. So actually, so our guess was too high. So we guessed, hey, this is 2, this is 1. If we just guess it's just half of this, well, that guess is too high. And that means that our change in length would actually be too much change in length. Where actually this thickness dominates. It is very, so if we did have this scenario where it was 2 inches here tapered to 1, it's very synonymous with maybe like 1 1/4. You know what I mean? So what's 1 divided by 1 1/4? That would be a 0.8 multiple. Where let's do this. This is going to get 2.5 divided by 3. That's going to get a 0.83 multiple. So now we have change in length is PLET. And I should have put this multiple out there, but 0.83. You know what I mean? So given that B2, this is the scenario where B2 is 2 and B1 is 0. So this is your change in length. Hell yeah. Okay, hell yeah. So now we just kind of figured out we could do any scenario with this. Let's try to do it one more time. I got to throw some more juice in my camera. Catch you on the flip side. Alright, hell yeah, we're back. And let's do this scenario where we have, we're going to do 5 segments. And then I got to burn off more sheets of paper for our problem. 4. All right, 5. This is going to be B2. This is going to be B1. And we're going to use that same scenario to try to get our answer a little bit better on both these. The scenario where we taper to nothing, 2 to nothing, and then the same taper where we taper from 2 to 1. Well, we already did the 2 to 1. We know that works. So yeah, we'll use our formula for any B or B1 over B2, and then we'll try that one out. Okay, so hell yeah. So this one is going to be B2. This one is going to be B1. That's the thickness or the height. And when we're saying that's the height, and we're saying our area is equal to the thickness of these, because they have some sort of thickness. You know what I mean? I should draw that in, but there you go. And that's going to be T times H, thickness times height. Okay, hell yeah. And we know that this one is the halfway, so this is going to be B1 plus B2 divided by 2. Okay, so now that's this value. But now to find the halfway point over here, you got to take this plus this and then divide that by 2. So I'm going to make this a little simpler. I'm going to say that this value is 1/2 B1 plus B2. Cool. So now we're going to add those. We're going to go B2 plus 1/2 B1 plus B2. And we're going to divide this whole thing by 2. And even just right here, I can say, so maybe I shouldn't have done that. And I can say, hey, this is the same thing as B2 plus 1/2 B1 plus 1/2 B2. Well, I'm going to say 1 B2 is 2 over 2 B2. So now I can see, hey, these are the same, and I'm going to have 3. So I'm going to have 1/2 B1 plus 3/2 B2 divided by 2. You know what I mean? So dividing by 2 is 2 over 1. The same thing as multiplying by 1/2. So there you go. So we're going to multiply that through, and we're going to get 1/4 B1 plus 3/4 B2. Hell yeah, and I think I did everything right, so that's going to be this one. This one's going to be 1/4 B1 plus 3/4 B2. I didn't really have to simplify this one down, but it was just kind of fun. Because the second I turn this into 9 segments, then I have to multiply these two together. And hell yeah, I might want to do that. Alright, so let's go B1 over 2 plus B2 over 2, which is this. And we're going to add it to B1. Cool, and that's going to be 2 over 2 B1. Divide that by 2. Alright, so the B1s are going to add. So now we're going to have 3 over 2 B1 plus just that B2 over 2. Or just 1/2 B2. And then dividing by 2 over 1 is the same thing as multiplying by 1/2. And now I'm going to have 3/4 B1 plus 1/4 B2. There you go. So this is going to be 3/4 B1 plus 1/4 B2. And it is very, very similar, just opposite. So I know I'm doing good. And now our change in length, we have 5 segments. So this is L over 5. So I'm going to say, and here's the equation, change in length is PL over EA. And this is just so good to actually, you know what I mean, doing this, you get so much more familiar with the change in length formula. And I actually got to start my clock. All right, hell yeah. I started my timer, and so booyahs. Yeah, it just gets you so much more familiar with the equation of change in length. Force, length over modulus of elasticity, area. All right, so we have the force P, but we could just say, hey, this is ET, but now we have the length is going to, and we'll do the length right there, but we have a multiple. This is your length divided by 5. So there you go. So there's your 1/5. And now our areas based on the height, you know what I mean, it's going to be for each of these. So you're going to have 1 divided by B2. Plus 1 divided by, and I'm just gonna go 0.25 because in my calculator I'd lose my mind doing fractions. So there you go, plus 0.75 B2. So that's the first one, and then we're gonna go plus 1 divided by 0.5 B1 plus 0.5 B2. That's the midpoint. Plus 1 divided by 0.75 B1 plus 0.25 B2, and then just plus 1. So there you go. So now we can throw in the example where this is 2 and it tapers to 0. And so we would have 1 divided by 2 plus, well, this is 0. Oh, maybe I should have done fractions, but nah, we're good. So now we're going to say this is 2, so now we got 1 divided by 1.5, because 0.75 times 2, there you go, plus 1 divided by, this is 0, this is 2, so 1 divided by 1, cool, plus this is 0, this is 2, 1 divided by 0.5, cool, 1 divided by 0.5, so we have a little scenario going on, and then this is just 1. Well, this is just B1. I'm sorry, this is B1, so that is the equation. I'm sorry I put 1 there, because that is not true. This is B1, and B1 in this scenario is 0. That would have thrown me off. Okay, hell yeah. And then we're going to multiply that by 1 over 5. We're trying to shoot for that 0.8 number. We'll see if we actually get close. So now we have, and let's try to do this mental math. We got, nah, I don't want to. We're just gonna do it. So we got 0.5 plus 1 divided by 1.5 plus 1 plus 1 divided by 0.5 plus 0. Hell yeah. Divided by 5. Hell yeah. And we get 0.833 repeating. And that's literally the same guess that we got before. So on that scenario, we don't get a more accurate guess. So let's use these two equations for the 2 over 1 scenario. So we're going to say, hell yeah, this is going to be 1 divided by 2 plus 2 divided by 3 plus 1. You know what I mean? Hell yeah, and this is going to be divided by 3. So this number is 0.722 repeating. So now we're going to use that same equation. We're going to go 1 divided by 2 plus 1 divided by, this one's going to be 0.25 plus 1.5. There you go. Plus 1 divided by, this one's going to be 0.5 plus 1 plus 1 divided by, this one's going to be 0.75 times 1 plus 0.25 times 2. Alright, hell yeah. Plus 1 divided by 5. And yes, we get that 0.707. So we do get a better guess on this one. But that's fascinating. I just learned that just from these two equations. That this is getting us a better estimate. But when this is 0, our answer is 0.83 repeating. So maybe this says that, because this should give us a better estimate of what's actually happening in this ideal scenario of a perfect triangle. Just represented with this, you actually get the right answer. So that is fascinating. So this answer definitely converges it basically, for whatever reason, I'm just guessing that this answer is 100% right. But we'll find out, because we're actually going to get we're gonna get an equation that uses kind of natural logs. So and I'm not going to explain what the hell natural logs are, but it's basically just a fundamental of calculus. Is that we have this scenario where when we divide by area, and area is a function of x, and x is just a linear x to the 1. Well, 1 divided by x to the 1, if you integrate that, you're going to get, well, 1, that's at x to the negative 1, so you're going to get x to the negative 1 plus 1 divided by negative 1 plus 1. You know what I mean? And then you're going to get x to the 0 divided by 0, and you can't divide by 0. So you know what I mean? You would get a constant divided by 0, and you can't have that. So we get the natural log. Okay, hell yeah. So now let's get on to it. I'm going to print off some more sheets, let my camera cool, and we're going to do this problem. And we're not going to solve the strain energy. It's identical, but I would just, like I said, I make long videos, and it would take me another 4 hours. But we are going to do the elongation. And, you know, instead of cutting it up into segments, we just want one fluid formula. But the cool thing is, we've played around with this enough. So anytime you get this, you want to relearn calculus. You know, no matter, even if you're like really good at calculus, if you're really good at calculus, you can just do this faster. But definitely take the scenario, chop it in 2, chop it in 3, chop it in 5. Exactly what we just did. Throw different scenarios at it. We even came up with our series equations. Before calculus, you would have just done this anyway. You know what I mean? you'd have been like, I don't know how to do calculus, but I'm just going to say, hey, the answer is approaching the answer that I want for some reason, because we're just chopping it into slices. You're basically inventing calculus underneath your nose, before your eyes. All right, so hell yeah. So let's print off some more and then do this, and then we'll integrate it. Oh, but the reason why I mentioned that is because the second you start to do those integrations, your mind might melt, or you might miss a negative to a positive, because you have to integrate on some sort of line, and you might mess that. There's so many things you mess up, and in the end you might get an equation that has natural log in it, blah, blah, blah. But if you can't throw those initial values in, like B2 is 2 and B1 is 0 or 1, and get these same answers or very close to them, that's going to be your check on reality. And if you don't have a check on reality, well, then you're just doing math for math. You know what I mean? You always want to do math where you kind of understand each step along the way. All right, hell yeah. Let's throw some more time on the clock and catch on the flip side. All right, hell yeah. So let's dive into this and find out the calculus equation that we need to use to find the actual change in length. Because basically we're trying to find the change in length as FL over EA. And we want to get this equation as a change in length as a function of B1 and B2. Cool. And obviously everything else is going to be, these are only changeable variables. The thickness T is constant. E is constant. We're going to do a force P, and then L, it'll be an equation. It'll be an equation as a function of all those components. But yeah, so I guess it is. But definitely B1 and B2 are variables that change the area. So those are the ones that we're going to be integrating with. And so let's get to it. All right, so we're going to say that change in length is P L over E T, and then we have height. I guess we can call it height. So our height is going to be a function. So what we want to do is, I guess calculus says, hey, we actually take a slice right here, and I want to know the change in length of any given slice. And so I'm going to say, hey, this slice is a distance x over here, and this all has a thickness, you know what I mean? So this slice has a thickness t. I guess this thickness t there, and then some sort of height. And the height of this, well, we know, I mean, just based on observation, we know that h has to be bigger than b1, but then less than b2. You know what I mean? So whatever formula we come up with, it has to like have a check on reality. So that's our check on reality. And what are we going to say? We're going to say that this is a dx. You know what I mean? So we divvy this. This isn't even L over 100. It's L over 10,000. 10 million. It's so small it's dx. But anyway, and then we're going to sum all those up. And, we do that by using, I got a bug on my leg. All right, heck yeah, back at it. So we know that, so how we use the integration is that we know that if we find the change, so we found the change in length of 3 segments and then 5 segments. But this is saying if we can find the change in length of just any given segment with dx, we can use, the invention of calculus to sum them all up. So, I mean, we summed up 5 of them, but that took some time. But now we're going to say, hey, if we sum up an infinite amount of chunks, how do we do that? And so I swear I don't know. But no, we kind of do. So we say that the length, so if we take this if we have this little chunk, so let's say we have this little chunk and it is dx, and we just want to find, if the problem just gave us this, it says, hey, we have a very thin slice of steel, and it has a thickness of t, and it has so this thickness, the length of it though, the length is dx. So the length is dx. and we want to find the change in length due to, and we're going to put the same load on this, you know what I mean? And we want to know the change in length of this little segment. Well, we're going to say, hey, the change in length is force L over EA, which is FLET times the height. And we're going to say, and so this has some height too. And we're going to say this is F, the length is dx, and then E is a constant, T is a constant, but then the H, well, we don't know H, you know what I mean? We just know that it's somewhere, you know, we know it's somewhere between B2 and B1. And only when X is L over 2 is it going to be halfway between B1 and B2. But basically what we're getting at is that this H, this height is going to be a function of X. So now we have a dx and a function of X, and we've found the change in length of a small slice. Okay, so this one's going to be a microscopic number. If it was L, you know, it'd be 1/10, 1/100th. Anyway, and then you would integrate. You know what I mean? So then you would integrate from X is 0 to X is the full length, and then you would sum up all those change in lengths due to small slices, and then you would get your answer. The answer would be the change in length total for this setup. So the hardest thing is to find an equation for height that's a function of X. So let's grab another sheet of paper, because we can kind of make this fairly simple. Because all we need to do is find we need to find an equation for this line. So see that line right there? If we had an equation for that line, that would be useful. So to make that make sense, I'm going to divide this in half. And so all we're going to do is find the equation for this line. And if we found the equation for this line, this is X is 0, this is X is L. If we found the equation for that line, and then we integrated between 0 and L, we would find the area right there. And guess what? And because the area of any slice is thickness times the height. Well, and then let's back it up. But if we find this equation, so we're going to find, this is going to be h of x, and if we find this equation, or I just call it y, you know what I mean? Just, hey, it's a line. It's y, and it's going to be, and we know the formula for the line is slope times x plus b, I'm just using that loosely. Y is equal to mx plus b, because b is, don't get it confused with b1 and b2, but b is the y-intercept. And so let's start there. Obviously, we're going to integrate and find the resultant of the area, and then that's just half, so we would multiply by 2. But let's stick with this equation first, because if we throw in any x, if we say x is equal to L over 2, we could throw it into our equation, and we would get this height right there. And then we know to multiply by 2 to get that height, and then that would be your height, that x, or height, that L over 2. So for that little segment, you know your height, and then that has to be between B1 and B2. Okay, so to get the equation of this line, we can say, hey, let's draw an XY graph. So here's your x, here's your y. This line hits the y-intercept at B over 2 divided by, so it's B2 divided by 2. So 1 half, and we're only looking at half this graph. And so that's its y-intercept. So cool. So we have this equation is mx plus b. We already found b. B is going to be b2 divided by 2, 1 half b2. And then our slope is rise over run. Now I would always write it like that. And then don't forget about, forget about negatives and positives for now, but let's just do the rise. So the rise between this point and that point is going to be, well, we have to basically add this and then subtract this. You know what I mean? So that would give the residual. So we would go up to 1 half B2 and then subtract this little segment, and then what you're left with is that rise. So you're going to go from, it's going to be a negative slope. It's a downward slope. But if you don't worry about the negative slope, you'd be like, hey, let's say it's a positive slope going this way. I just need to figure out what type of slope it is. So we're going to say the slope is, we'll throw in the negative right now, but it's B2 over 2 minus B1 over 2. And we're only talking about still half this, you know what I mean? We're drawing our line in there. We're just trying to find the slope of that line. And so we did. We found it. So now we can throw it into our equation. Whoa. See, that was where I messed up the first time, and I keep messing up because we just found the rise. So we found just half of rise over run. So the run is this L. So I mean, we're using just variables, but we're saying, hey, the rise is half of B2 minus half of B1, and it's a negative slope. So that's the rise, but the run is divided by L. So hell yeah. So now we're just good to go. And we can simplify this. We'll just say M is negative 1 over L, B2 divided by 2 minus B1 divided by 2. Okay, and let's throw it into our equation. So the equation, y is this slope times x plus b. So we have negative 1 over L, B2 over 2 minus B1 over 2 times x plus where it hits the y-intercept at B2 over 2. Okay, hell yeah. So now let's do a check on reality. Let's throw in, because this was our x value. We're saying x is, so we're going to throw x is 0, we should get B2. So let's throw 0 in right here. Oh, no, we're going to get 1 half B2. That's why it's like, hey, let's see what our equation was. Our equation is just this line if this is the midpoint. And that's going to give us half the height. So this equation, if we throw in x is 0, is going to give us half of B2 right there. Now let's throw in x is equal to L. Hopefully it gives us B1. So if we throw in x is equal to L, the L's cancel. Oh, and I should have distributed this negative anyway. So we're going to go, we're going to distribute this negative through here. You know what I mean? Kind of like foil the negative through. This becomes negative, that becomes positive, negative goes away. And we're going to get 1 over L, and then bring this to the front, B1 over 2 minus B2 over 2 times x plus B2 over 2. So if we throw in x as L, now the L's will cancel, and then look what we're left with. Negative B2 over 2 plus B2. So these cancel, and then you're just left with B1 over 2. So heck yeah. So this is an equation for half the height. To get the equation for the full height, we just need to take this and multiply by 2. So let's do that. So we're going to have y is 1 over L, and then we're just going to have B1 minus B2, x plus B2. And there you go. So this y as a function of x is the same thing as h as a function of x. You know what I mean? All right, hell yeah. All right, so we took 2 steps forward. We got an equation. Now let's take 2 steps back. Our change in length was going to be for each of those very small, you know, sections of dx, our height as a function of x, and so our length is dx, our height is x as a h function of x. So we just solved for that, and our thickness is t. So our change in length, or our very small change in length, do you say this is d change? I don't even know my terminology. But basically you're going to get FLEA, FLET, h is a function of x, L is a function of x. So now we're going to say this is P dx divided by ET h of x. Okay, heck yeah. And now we're going to throw this equation into there. So we're gonna say, and I don't know how to represent it over here, but in essence we'll take the integral from x equal to 0 to x equals L, and then that is going to give us the change in length. So the change in length total is going to be the integral of this. That's summing all those slices. Each slice has a width dx and has a height as a function of x. Cool. So let's grab a new sheet of paper, and we're going to say change in length is integral from x equals 0 to x equals L, p dx, e t h of x, where h of x is 1 over L, b1 minus b2, x plus b2. And we already did the check on reality, so we know that this is good. So let's throw this into our equation. Change in length is integral x equals 0 to x equals L. And we got p dx e t, and then let's throw that in. So L goes up top. I mean, we're going to have an L up top, you know, because this is just a constant. So, but down here we're going to get b1 minus b2 times x. Oh, and this whole thing is multiple. This whole thing is the area. So then we got plus b2. So this whole thing is essentially quote-unquote the area, because area is t times that h. So this is still just the height, but I mean this is why the area is a function of x. T is just a constant, and this L is just a constant, so we take those out. All right, so now we get, so let's see what this looks like. So we can take all the constants outside of the integrand, or is that what they say? So we got PL ET, and now we're going to have integral x is equal to 0 to x equals L of just dx divided, and I'm going to take this part to the front because we're going to find that useful. B2 plus whatever's in the parentheses, b1 minus b2x. Cool. Now we integrate this. And this looks very similar. So in the back of the book, we have the integral of, there you go. We have the dx, and then an a plus bx. So here's our answer. It's 1 over b, natural log a plus bx. So we just throw all those in. So I'm going to write this down. So we're going to have dx a plus bx is equal to 1 over b natural log of a plus bx. Heck yeah, we might have to write it down twice, because, but anyway, so this is going to be my b, so, and then this is going to be my a, and so heck yeah, so here's what we're trying to get it to look like, and it basically looks like that. So now we can just solve it. And so anytime you get the answer, obviously if you have like 0 to L, then you have to do the final minus the initial. Throw in the final value minus the initial value. And once we do that, we're just good to go. And if you do this, I mean, obviously this answer they say is plus a constant, but I mean, it's always good to explain what happens with that constant, because you'll have you'll throw in this value of L plus a constant minus this value of 0 plus a constant. So the constants will subtract, and then the constants, when you're doing a definite integral, just kind of get eliminated, wiped out. Anyway, all right, so heck yeah. So now we'll just throw that in. So we'll have our change in length is going to be PL ET times, heck yeah, 1 divided by b is going to be b1 minus b2, and then natural log of a is b2, plus I hope I didn't do this wrong, but that's going to be this term, b1 minus b2 x. Heck yeah. And we're going to evaluate that at L and 0. So first we evaluated at L, and then we yeah. So well, let's write this one down up here. Just make it nice and small. We'll go PL ET B1 minus B2, 1 over that, natural log, oh, I shouldn't have wrote it small like this, but B2 plus B1 minus B2 X, evaluated from 0 to L. Holy Toledo, I shouldn't have wrote it that small. So let's write it big. Change in length, PL ET B1 minus B2. So this is our 1 over B term. And then you have natural log, this is our A term, B2, plus B1 minus B2, this is our B term, times X. And we're going to evaluate it from 0 to L. So first you throw in L. Holy Toledo. Did I just skip? No, I guess I didn't. No. So right here when I had 1 divided by L, it was okay for me. It was okay for me just to leave it downstairs, but it is a constant. So I'm dividing by 1 divided by L, so that just brings it upstairs. But now when I go to evaluate this, I'll throw an L right here. Oh, bummer. Well, that's gonna drive me nuts. Holy Toledo. All right, let's take a step back. No, maybe we're good, but I don't think so. I think I made a mistake because the answer in the back of the book is always simplified. Yep, which is sometimes not helpful. Yeah, so let's take one step back, and that's just the facts of life, you know what I mean? So we had this equation, and I think where I got mixed up was sure, like this 1 over L is divided by the whole thing, because I said no. I'm sorry. It was no. So yeah, that's where I got messed up. My height equation was going to be rise over run. You know what I mean? So we had you know, basically the rise was B1 over B2 in essence, but we have to divide that by LX. And then and that's plus B2. So I'm glad I made that mistake, because you're just not going to be able to do these problems without making one mistake. And it's very important, more time on the clock. And it's going to be very important to catch your mistakes and see and how fast you can catch your mistakes. So let's just, you know what I mean, we got through the integration, but I think we can just do this kind of rapid fire now. So we have change in length is PL ET times H is a function of X, and then L is going to be a function of X. And our height equation is going to be some sort of mx plus b. Our b, if we draw that line, is going to be b2 over 2. And our slope is going to be rise, which is b2 minus b1, but divided by 2. And that's going to be negative slope. But then that's rise divided by run. So we're going to have this 1 over L term. And then this whole thing is going to be multiplied by X, you know what I mean, plus B2 over 2. So this is the entire equation. So now we're going to clean this up. We're going to factor this through. So we're going to get, well, and then we just double it anyway. So we can double it by getting rid of that on both terms. And so we're just kind of going through this fast, because once you did it once, you can kind of make rushed observations just to get back up to speed. So this is going to be b1 minus b2 in parentheses, and then we're going to have x over L. And keeping this together will be very important in the end, and that's why I got into a hiccup, especially since the answer in the back of the book is just real nice and real concise. But now if we throw this, if we throw in, so now here's our equation. So if we throw in x is 0, this multiplies through by 0, and we just get the height over here. If we throw x is L in here, and that's where I did a very bad job of, because I messed up, it probably wasn't as clear. If I throw L in here, L over L is 1, and now we get b1 minus b2 plus b2. The b2's cancel, and we just get the height over here. So cool. Now we have an equation that's the full height. So if we say, hey, any value of x will give me the full height. And so heck yeah, so that's this piece. And then this Lx is just a small slice because we're going to integrate. So to get change in L, we're going to have the integration from x is 0 to x is L. And then once we do that, we're going to P, E, T are our constants on the outside. Integration x is 0 to x is L. Now we're going to have dx divided by, we're going to bring the b2 in front because that's going to be our a value, and then we're going to have it plus, we're going to have b1 minus b2 x over L. So sorry, x over L. Keep those together. And this is going to be, and right now, we can just bring this L right there because that'll make more sense. And this is going to be times x. So now we have something that's dx a plus bx. So how do you integrate that? Well, that's going to give us 1 over b natural log of a plus bx. We've already done that. So now, you know what I mean? And the more times you use the integral and just like, hey, just spit it out. So if you see this pattern, it's always good to double check, but you can just, spit it out faster. And now we're gonna evaluate this from 0 to L. Okay, so let's do that. And we're gonna have the full change in x is our constants, P, E, T outside the box. And now we're going to have 1 divided by b. That's going to be our b term. See, now our b term is this. So let's circle the b term. It is b1 minus b2 divided by L. It's this whole thing. So there you go. So we got b1 minus b2 divided by L. Natural log. Our a term is b2 plus, same thing. Our b term is b1 minus b2 divided by L, all times x. And now we're going to evaluate this at 0 to L. So now just visually we can throw this in. We can throw in L. The L's cancel, and we'll get b2 minus b2, plus b1. So this will just be natural log of b1. But then we're going to multiply, if we throw in, and then this will just be L over b1 minus b2. Cool. And our second term is going to be minus, throw in the 0 term. So we're going to throw in 0 here. Cool. We'll just get natural log of b2. And then we'll have this same constant out front, L up top divided by b1 minus b2. So our final answer, and I might just shift this up just a little bit because we'll rewrite it. Essentially you'll get b1 minus b2 divided by L. Natural log b1 minus that same thing, b1 minus b2 divided by L. natural log of b2. And it's a property of natural logs that if you have some, so the constant's just out front. So basically we're just going to have a big constant. That's going to be our constants. And anytime you have a natural log of, let's say 2 minus natural log of 3 is the same thing as natural log of 2 divided by 3. You know what I mean? You don't have to do it. You can just be done right here. This is our equation for change in length. But we can use this, this parameter. And then we lost all our constants too in this whole thing. So change in length will be our constants, P, E, T, and then you know what I mean. This constant, which would be oh, and then I kind of messed up. Yes. This whole thing is 1 divided. You mean holy Toledo. So this whole thing is 1 divided all this. So at the end of the day, I could have flipped this around to be L over B1 minus B2. This is basically this is that constant that I was talking about. So we're going to have L divided by B1 minus B2. Yeah, this is a 1 divided by all this. Heck yeah. And then you're going to get natural log of this B1 divided by B2. So you got B1 divided by B2. There you go. And then this is our equation. You know what I mean? And cleaned up a little bit more, you're going to have PL ET B1 minus B2 natural log of B1 over B2. But let's say, you know how we got like, because I got this equation for half. You know, I spent a lot of time getting the equation for this at a half. And you know, this seems complex. And then at the end of the day, I could just say, hey, change in length is FL E A. And then I know this equation as a function of x is only half. And so I could just double it out here. And because that's what I did at the beginning. I'm just like, well, I'm just going to multiply by 2 once I'm done. But if I didn't simplify, you know, this equation might just get a little bit more, you know, involved. It can still generate the same number. So let's do our check on reality. We're going to throw in those 2 scenarios where we have 2 and 1, and then we have 2 and 0. So that's going to be... And all this is constant, so basically we just need, and this is so we're going to have basically natural log of 1 divided by 2 multiplied, and then divide that by 1 minus 2. There shouldn't be a negative here, so that's a bummer. This should be B2 minus B1. Should we try to find our error there? Yeah, before we do, let's do that. And then we can maybe draw a bigger picture of this bar. So we have we have B2 here and then B1 here. And then we're going to take the halfway point. We're going to say this is our y-intercept. So this is B2 over 2 and this is B1 over 2. So our y-intercept, so our equation is mx plus b. And I got to throw some more time on the clock. Alright, heck yeah. So our slope is going to be negative. And our rise is going to be b2 over 2 minus b1 over 2. Is that right? Because that's where I feel like I'm getting messed up. So yeah, it's basically, we're just basically trying to find this. This is our right. This is our change in y. Our change in x is just L. And then our change in y is like, hey, go up b1, but then minus this b1 over 2. So, I mean, yeah, b2 over 2 minus b1 over 2. It's kind of hard to say. And so this is our rise, and then divided by L. So there you go. But yeah, did I get... And then our y-intercept is plus b2 divided by 2. So we're going to FOIL this negative through, and we're going to get B1. And then I'm just going to multiply by 2 because there's twice the height. So I'm going to get B1 minus B2 divided by L. That's going to be the slope plus B2 over 2. And this is going to be X. So that's the equation for that. And our natural log. Oh, yeah. So yeah. This is where, because. Oh man. Yeah. How do you get that? So yeah, given this integral, this is our b, so you're going to get 1 over, I mean, you flip it around, you're going to get L b1 minus b2 natural log of b2 over 2 plus, this thing, b1 minus b2 over L times X. And then we're going to evaluate this from 0 to L. Yep. So, and this is just B2 because we already multiplied it by 2. Apologize about that. Yeah, and then you're going to get B1 minus B2. So that's for sure, because if you throw in L here, you're going to get B1 minus, you're going to get just B1, natural log of B1. And then minus, when you throw in 0 here, you're just getting natural log of B2. Alright, and if you do the negatives, it's going to be... So yeah, maybe I'm just right and I'm just overthinking things. But why am I messed up on here? Because this is going to give a negative value. B1 minus B2 is going to give a negative value. Bummer. And yeah, we're integrating from here. Well, am I getting messed up here? Because if we integrate from x is 0 to L, no, I don't think I'm getting mixed up there. My equation starts here. My equation starts at the 0 y-intercept. Oh, well, let's go back to our equation for h. You know what I mean? Because we said that boiled down, this was going to be B1 minus B2 divided by L plus B2. Yeah, and then this is going to be X, X divided by L. But yes, this is going to give us a negative value for this. Oh, perfect. Yeah, holy Toledo. Well, what's the natural log of 1/2? Oh, there you go. Alright, more light, more... Alright, hell yeah. I just totally forgot that natural logs can be negative. You can't have a natural log of a negative number. This is nonsensical because natural logs are a graph that are like this. And then here's 1. And, or is it 1? So natural log of 1 is 0. Yeah, natural log of 1 is 0. So yeah, we were totally right. I was looking for... I just don't know anything about natural log. Well, no, I do know a lot, but it's just when you... So this problem is so good because it involves calculus and natural logs. You know what I mean? When you do the integration, you get a natural log, and then you need to know something about natural logs. And So yeah, so let's write out our equation. So we have the change in length is our constants, P, E, T, and then we're going to have this L, you know what I mean, our 1 over B1. So that's going to be this, length over B1 minus B2, and then natural log of B1 over B2. Hell yeah. So when we have the scenario where this is 2 and this is 1, and then we have the scenario where this is 2 and this is 0. Okay, so the first scenario, we're going to have natural log of 1/2. I just forgot that this is going to give you a negative number. And then we're going to have L. So these are all constants. So cool. We're going to have change in length for this scenario is going to be PL ET. But now we're going to have 1 divided by... and then this is we're going to have 1 here, 1 minus 2. So this is going to be -1. So heck yeah. So basically, whatever the natural log is, so natural log of 1 divided by 2 is -0.693. And then we multiply by negative, 1 divided by -1. So this is basically multiplying by -1. And so we'll get 0.693 PL over ET. And our equation seems to be doing right, because didn't we say this was close to, I mean, if we first guessed like 0.7, I forget, 0.79, but then we got 0.707, and now we're getting 0.693. And this is exact. I mean, this, if the equation works, this should be 100% exact. So now let's compare it to this scenario of 2, 1. So it's always, we started with 2 scenarios, we're going to end with 2 scenarios because we need to check on reality to make sure this equation actually works. So now you're going to get natural log of, well, B1 is 0. So you are going to get natural log of 0. Natural log of 0. Oh, see, yeah, it blows up. And you can't, natural log of 0 is, so this equation just can't do it. You know what I mean? So here's your natural log equation. Here's 1. And then here's, x is 0, or this is x, this is y, this is 0, 0. But that's why this equation blows up, because you can't throw this scenario into this equation, because it'll blow up. So I guess I can't do a check on reality of that equation, actually. And maybe when we segmented it up into segments, our answer was pretty close. But we could get close. We could say this is if this is 2, we could say this is 0.02. So let's try that. I mean, basically we're trying to get to 2 divided by 100. And then that essentially, I don't know if it breaks it up into 100 pieces or whatever, but yeah, you're just not throwing in, you can't throw in natural log of 0, but that's why natural logs are brilliant, because you can throw this scenario in, and it'll give you basically, well, I'll show you. First we'll throw in, we'll throw in this one, and then we'll throw like 0.2, and then you'll see that 0.002 gets us even closer to the answer. All right, more time on the clock. All right, heck yeah, home stretch on this check, and even using this equation with natural logs. So we're going to have, if we throw in, well, let's get our equation one more time. Change in length, all our constants, PL, ET, and then we're going to have 1 over B1 minus B2, natural log of B1 over B2. And just to make sure, we're not doing, but that's the thing, we've already used it kind of once, and we basically realized that we have the right answer. And so here's the equation in the back of the book. And it's this one so we have PL over ET divided by, this one says B2 minus B1, natural log of B2 over B1. But those scenarios are equal and opposite. So, you know what I mean? So let's write their equation, because we can show that our equation is an identical. I think so. B2 minus B1 it just makes more sense to do it this way. And I'm sure there's a property of natural logs that say if you flip these over, then you have to flip the constant. I don't know, but this is B2 over B1. That's what they have. So now your natural log will be a positive, and just to make sure you see this, B2 over B1, B2 minus B1. And that makes sense, because we ran into the issue where, hey, we're getting a negative, you know what I mean? And we didn't really like that. So now we'll throw in the scenario of 2 and 1, so 2 and 1, and then we'll get natural log of basically 2 over 1, which is natural log of 2, which we know to be like 0.30, is it 0.301? Natural log of 2 is, oh no, I'm way off. I don't even know what, holy Toledo. Oh, base 10. Yeah, natural log base 10 of 2. But yeah, we're doing natural log on the base e. So yeah, I don't have that memorized. I know how to convert between the two, but this is going to be 0.693, basically our answer, because 1 divided by 2 minus 1 is just 1. And yes, you get the same answer. So we'll use this equation, so then we don't have any negatives. And we'll throw in the scenario where this is 2, and then we're going to go all the way down to 0.02. And so we're going to have our constant PLET. We're going to have 1. We're going to have 2 minus 0.02 times the natural log of 2 over 0.02. Okay, heck yeah. So now we're getting somewhere. And this scenario, we thought it was going to be like 0.83 repeated for our PLET. All right, so natural log of 2 divided by 0.02. So this is going to be 4.605 multiplied by 1 divided by 2 minus 0.02. This is going to be this whole thing is going to be 0.505. So we're going to multiply these two together. Whoa, we're not getting, oh, no. No, we're definitely, that is not what I wanted. Okay, so let's slowly start decreasing this. You know what I mean? So we're gonna say, hey, we're gonna go 1 divided by 2 minus 1. Get some more parentheses in here. Times the natural log of 2 divided by 1. And so we get that 0.96. So we're going to play around with this. We're going to switch this to 2 to 0.5. Because we're getting closer to, instead of 0.0, we're going to get this to 0.5 and see if we see if that helps. So we're going to get 0.5, and we get we get 0.92. Now we're going to go to 0.25, or we'll just go 0.2. 0.2, and we get 1.27, and then we go to 0.1, and then we get 1.57. Okay, and then we'll just keep going. 0.01, and we get 2.66. But that doesn't make, for whatever reason, that doesn't make sense, because it seems like the elongation, yeah, so this equation is not accurate. I don't know, man. That's interesting. So is there some applications where this equation's not working? Because we'll make them, and maybe I'm getting confused by calling this 2, but I don't think so. Because if you had the max, oh no, we're getting increasing elongation. Yeah, no, that's right. So we can just go with it. Yeah, it's this is 2, but this is 0. So we said, hey, we're gonna have infinite elongation here. Like this is just like a wire. You know what I mean? So if we just had, if we had a wire that was 0.25, in height, then we would throw it into our equation. We would get change in length as PL over ET 0.25. So that would be change in length of 4 PLET. You know what I mean? I just got confused by doing the scenario of like, I don't know what scenario I actually, yeah, in the beginning, I don't know how I modeled this scenario at all. Like chopping into 3 sections, I don't think that was, or just chopping into 2 sections and say this doesn't elongate. But no, that was the worst. That was a dumb thing to do, because this section is the section that elongates the most. So if we did take if we took just a quarter inch, a quarter of the height, then we would get a lot of elongation. So with this 2 to 0, we can still throw it in. We should be approaching a value. And let's just keep going with it by adding zeros. Oh, that didn't work. There we go. So I think we're all set here. Oh, and maybe I had it messed up. So let me type this in again. 1 divided by 2 minus 0.0001, and then I guess all multiplied by the natural log of 2 divided by 0.0001. Yeah, and we get 4.95. But if we continue on this, I think the number just keeps going up. I don't know if it goes to 6. Yeah, so if we keep doing this, I think it's just going to keep going up. So that might not be a good representation for that one. Let's write this one more time. PLET 1 over B2 minus B1. I'm going to make a separate video and try to model this scenario and see what the right answer is. Because I swear this equation doesn't work for something that's tapered to a point. And that's why and that's probably, I think they explain that, because they say, hey, this taper has to be fairly, you know, it can't be too aggressive. But here's our equation. And so if our taper is like, let's just say this is 1 inch, and we'll go back to our other scenario where this is 0.9. So now we're going to have natural log of 1 divided by 0.9. That's going to be natural log of 1.11 repeated. And then we're going to have 1 over 1 minus 0.9. So that's going to be 1 over 0.1. So that's 10. So we're going to get 10 natural log of 1.11. And I think, and I always like to do that just to make sure my skills are getting better. 1.11. And we're going to see if that's 1 divided by 1 minus 0.9, that's 10, times natural log of 1 divided by 0.9. And heck yeah, so we get 1.05, which makes sense. If this was 1 all the way, you would get a change in length of just a factor of 1. But because this is slender, you're going to get more change in length. Like we said, the more slender this gets, the change in length gets bigger. All right, hell yeah. All right, that's it. You know what I mean? I think I'm done with this problem, and you know what I mean? Just to show you the problem in the end. So if we know that because this is more slender, you're going to get more change in length had the whole thing just been the same thickness all the way through. If you chose this thickness and went all the way through, you're going to get a definitely smaller change in length. But the more this is tapered, heck yeah, you're definitely going to get an increase in change in length, you know, by a factor of, and it could be, well, let's go to our equation. You know what I mean? If this is, let's say this is 4 to 1 ratio. You know what I mean? Using these as whole numbers kind of makes sense. And we're going to get 1 divided by, we're going to get 1 divided by 4 minus 1, natural log of 4 divided by 1. And you're going to, oh, shoot. Oh, well no, that's a bad representation. If this is 1 and this is 0.25, there you go. So this is a unit height, and so that'll make more sense. And then you're tapering down to something that's approximately 0. So even in this scenario, you're going to get 1 divided by 1 minus 0.25 natural log of 1 divided by 0.25. So in this scenario, you get a multiple of 1.84. So there you go. And then that's a decent taper. 1 to a quarter. It'd probably be the most taper that you would want, and you can basically double your change in length from given that this was your initial cross-sectional area. Like your change in length is FL over EA. With this, with the taper, you're going to have a change in length with a multiple of 1.84 FL over E, the area, this being your initial area. So there you go. So that's kind of showing how this equation kind of works in general. We used the equation where this was 2 and 1, and we were getting a multiple. Is that the same thing as this is 1 and this is 0.5? I think it is. So let's try that. So we're gonna have 1 minus 0.5, and then we're gonna have 2 divided by. I'm sorry. Yeah, no. 1 minus 0.5, and then we're going to have 1 divided by 0.5. No, that gives us a totally different answer. Oh, that is fascinating. So I mean, whatever you choose for your two initial values will, you know what I mean. It's not necessarily a factor, you know what I mean, of PL over ET. It kind of is, because you have, the reason it is because, hey, your thickness might be in inches. So, you know what I mean, if you choose 1 inch height over here, you know, that's also a unit of height. And then this over here, you know, would be some sort of lesser amount of that. But anyway, yes, so, but I guess it is cool that you can throw in any value of B2 over B1 within reason, because obviously this blows up, this equation blows up when this value gets small. And I think some of the books say that. It's like, hey, your taper has to be fairly, you can have a small value over here, but that means but your taper has to be, I mean, if you have a small area on one end, your other end, you know, is still, maybe you have a really small area, but this is just 2 times that small area. So your ratio between the area here and the area there is just a reasonable taper. The second your taper gets too much, this equation starts to not work. And, you know, the force that you're applying probably can't get evenly distributed through your tapered, you know, material that how it's shaped and stuff. All right, so man, this was a good video. I'm glad I kind of went through it all the way. I don't know if it's a 2 to 3 hour video, but I'm satisfied with it. I learned a lot, and I took my time with this one. I had to go back to the drawing board a couple times, but in general, change in length was P, L was a function of X, and then E, and then our area was a combination of 2 terms, thickness, which was a constant, but then we had our height as a function of X. But that's just tapered one way. Like I said from the beginning, this thing could be tapered 2 ways. It could be tapered like this, but then this could be thick here and then tapered down like there. You know what I mean? So to solve this problem, hey, now your thickness is a function of X. So there you go. Length is going to be a function. So we're going to say, hey, we're going to take our, you know, we're going to find that slice, because we're going to take this slice out, And it's cool. Like you can have a whole problem that says I have a really thin slice of steel and I'm putting a force and it's going to be evenly distributed on this slice. I want to know the change in length. And guess what? This has a width of dx. Or I'm sorry, the length of this is dx. So there, I want to find the change in length of that. Well, I know my formula is FL over EA, so that's going to be the force P dx divided by E, and then I'm going to have T as a function of X, H as a function of X. But then I'm going to say, hey, this is actually a composite of a bigger thing, and it has a value from 0 to L, and then I can integrate 0 to L, and then there's your dx term. That pops out of integration. You know what I mean? If you integrate dx, you integrate that, it's just going to go to x, and you're going to evaluate it between 0 and whatever, 0 to 1. So heck yeah. Booyah. But yeah, you get to learn a little bit about calculus. Anytime you can learn just a little bit more about calculus, it's useful. And especially if you can put some parameters on where it's just like, yeah, I kind of want to know what's going on with the calculus from simplistic perspectives. Yeah, I really do want to chop up this scenario up one more time. And maybe I will make this kind of a longer video. And we'll try to chop this one up and see if we can get similar answers to this equation to kind of match. Alright, heck yeah, catch you on the flip side. Alright, heck yeah, let's burn this one down. So we're going to do that scenario, you know what I mean, of tapered. Like all the way to a very small taper, we have a length L. So, and which one should we do? Did we like the fact that we did this 2 and this 1? I think for the ratios it kind of made more sense. And well, no, I mean we want this to be 2 and this to be 0 in essence. And if we throw 2 and I don't know, I think we just need to start doing it. So the first setup is 2, and then we're going to taper down to just half that. You know, I think so 2 to 1. So that's going to be the first setup, and then the next setup would be 3 segments. So we would do 2, 1.5, and then 1. I guess this has to go down even farther though. So we could do this one we'll have to do 4 steps of even steps. So we'll do, like, if we did 4 steps, we would go 2 1.5 1.5. Okay, so that makes sense. And then we'll do 8. So let's just say we have 8 steps. 4, 5, 6, 7, 8. So we would have 2, and then we'll drop in half. So 2, 1.75, 1.5, 1.25, 1.75, 0.5, and then 0.25. There you go. 1, 2, 3, 4, 5, 6, 7, 8. Cool. So we'll do that. We'll do that one for sure. And then that might round us off. If we did 16, if we tapered from, so we have 2, we got 4, 8, and then if we chopped it up into 16 pieces, we would have 2, 1 point, oh man, 0.125. I'm going to put 125 stored as x, so we would have 2 minus x minus x. So we would have 2, 1.875, 1.75 minus x. I don't know if we're going to get that far. If we do, then hope, because I don't even think we'll have a converging, I don't even think it'll converge. So this is going to be L over 4, this is going to be L over 8, L over 16. Okay, so now with our equation, change in length is PL ET. L is going to be this first one. We're going to do 1 over 4. And then these are our heights. So for our equation, it would be 1 over 2 plus 1 over 1.5 plus 1 over 1. I'm sorry, plus 1 over 0.5. Okay, heck yeah. So let's see what this generates. So we're going to have 0.5 plus 1 divided by 1.5 plus 1 plus 2, because I know this is 2. Alright, divide by 4. So even in this scenario, we get 1.04. You know, that's our multiple. So now we'll go to this scenario. This is going to be, we'll have to divide by 8 in the end, but we're going to have 1 divided by 2 plus 1 divided by 1.75 plus 1 divided by 1.5 plus 1 divided by 1.25 plus 1 divided by 1 plus 1 divided by 0.75 plus 1 divided by 0.5 plus 1 divided by 0.25. And then divide that by 8. And right here we get 1.35. I'm going to throw more time on the clock. Alright, heck yeah. So let's throw this scenario into our equation. So we would have 2 minus 0.25. Okay, so we're going to inverse that times natural log of 2 divided by 0.25. Okay, heck yeah. So this generated 1.18. That would be the actual answer of this setup. But this is what we get because this is well, I don't know why this would be actually smaller, but oh, that is fascinating. It seems like this number should be smaller, but okay, let's do this one. So if we do this scenario, if we have 2 and go down to 0.5, and here we would have 2 minus 0.5, and then we're going to invert that, multiplied by natural log of 2 divided by 0.5. Alright, and this would generate 0.92. So that is, I'm kind of bizarred out by, well, let's just if we drew that in, oh man, it seems like this number would be a higher change in length, but it's not. I don't know how to prove that. Anyway, but yeah, we're close. But yeah, as this tapers down to 0, I mean, I guess we could try this one, but it's just too many numbers, and I think I'm done with this problem. I would probably just want to throw it into Excel just to, I don't know, just to kind of throw a check on reality to see if this thing, I mean, obviously it's going to match this equation, and this equation does blow up if B1 approaches 0. You know what I mean? This goes way high, and even just dividing it by this won't be enough. You know what I mean? I mean, because if this goes to 0, you're just going to have B2, right? You're going to have 1 over B2 in the end, but then this will blow up. So if we go, yeah, this goes to infinity. So the natural log of a really big number, you know what I mean? Natural log of infinity is still infinity. But maybe not. Or, I mean, holy Toledo. But yeah, we just showed that if you have natural log of 2 divided by 0.123456789 okay, and then we're going to divide that by, or multiply that by 1 divided by, basically 2. You know what I mean? Yeah, you're going to, yeah, this equation I'm not too satisfied with. So there's a parameter in here that just the mathematics don't really jive due to actual reality. because I think this will be closer to reality. I don't know, I would like to throw this, I would like to use this equation and then throw these segments into Excel. Because yes, if you have all these segments of different diameters, this should be a pretty accurate way of determining the actual change in length of the setup, and just to see if these two diverge. But I would have to throw it into Excel to see if these two equations diverge. This is fascinating. It seems like if you do integrate and you get a more precise equation, that you'll get a more precise answer. But this does have limitations because it blows up. Or maybe it doesn't necessarily blow up. I just think it's inaccurate. I mean, because if this is 2 and this goes to 0, how could it possibly... I mean, your change in length of this little section ain't going to make up for... Yeah, it doesn't make sense. I mean, on average, this will just have a cross-sectional area of 1, and your change in length would be, PL over EA, or ET, as a function of 1. The fact that it can get up to a change in length of 11 is just absurd. So yeah, I'm actually going to throw this into Excel, and maybe I'll come back and see if I get any answers on that. But anyway, or we might be done with this video. So thanks for joining me, and guess what? That's a video. Alright, hell yeah. So I threw all this in Excel, and we'll get to that in a second. But yeah, we learned a lot. So what we want to do is we want to model, this shape from 2 to 0. And so we can do that by breaking it up. So we're going to break this up into 2 sections here. And then one will be just a 1-inch section to there. Okay? And had we just tapered, I mean, all we can do is say, hey, we're just going to mimic it as a section from there to there. Because this is 2 and this is 1, so we would throw it into our equation. Essentially, this is the only part of the equation that matters. But we would have, and we'll go 1 over, this is 1 over 1. 2 minus 1 is 1. And then we'd have natural log of 2. So hell yeah, that's going to be that 0.69. And if we just did it this way, we would have, because our area is going to be 1 over 2 plus 1 over 1, and then our length is going to be L over 1 over 2. You know what I mean? So this is how I throw into Excel. I say that this is going to be 1.5 divided by 2, so this is going to be 0.75. So 0.69 is this. So now the question is, why is this less than this? So if we start to model this, so at the end of the day we have something like this. We have 2, and then we have 1, same lengths, and then, or we would have something that would be like this, and that's not a very good drawing. Let's get a bigger drawing of this so we can just kind of see what's going on, and then we'll go halfway. So there you go. So we'll have a 2-inch bar, and then we'll divvy this up just so we're very symmetric, and then we'll have a 1-inch bar. So we can model this, and we said, hey, this section and this section, that'll be that 0.75 multiple. So why is the other one, so this is more, change in length is more than change in length is 0.69 for the actual equation. And let's get a straight edge on this, because we'll really be able to see it. So we'll get this going. Heck yeah, that worked. And then we'll get, move the paper. And then we'll get this going. Alright, booyah. So now what we'll see is that the natural log equation says this is 2 and this is 1, and it shows this taper, and you can see that when we cut it into sections, this section is more slender. So we're actually going to get more change in length out of this. We said if we have like piano wire, you can really stretch, or thin wire, you can really stretch and even see the stretch. So this section is much narrower than this section. You know what I mean? Even this tapered section is kind of wide right there, and then it's the same. So this section will have more change in length. And then let's take a look at this section. This tapered section will elongate because it's thinner. It'll elongate more. But because it's a relationship of 1 over area, these two will have a very similar change in length. But if we come back to this section, heck no. This section is way more slender. It's going to have way more change in length. And so this section is going to dominate the change in length. Because let's just say the change in length here is not half the change in length here. The change in length here is like, let's say the change in length here is just 4 times the change in length here. You know what I mean? This is just 1 time. And even if this is 2 times the change in length and this is times 1, you know what I mean? You still, well, didn't we say it's just not that? Yes, I don't know, but it's a 1 over area is the change in length. So there you go. You get like a 4 times multiple, or you know, your change in length. Yeah, I don't know how to say that, but heck yeah, because this last little bit is much more slender, you're going to get way more change in length than this tapered, and that's why this number. Making segments is always going to be higher than this number. Okay, so I think that's enough preamble. We're going to take this to Excel, and that's how we're going to finish this video up. We segment our length, you know, into we go from 2, then we go to 4, and then we go to 8, and then we go to, you know, we just go 16, 32, 64, and I think we even get up to 128. And we can see that the equation blows up. So the initial equation was this natural log, and if we have natural log of 0, if this goes to 0, well, natural log of 0 again, it goes to negative infinity. You know what I mean? So that won't, or no, it doesn't. Holy Toledo. Natural log of a really small number. Yeah. So yeah, I wrote this equation wrong. I don't even know what kind of sheets of paper I'm pulling out. But here's the equation. Yeah, b over 2. So if this goes to 0, you're going to have natural log of infinity. And a natural log of a really big number, well, this will just be a big number. So, you know what I mean? You can't accurately model what's going on here if you take this all the way to the point. It only works with slight tapers. You know, that's where this is going to work the best. Because even if you have heavy taper, like I said, if you have the force, you know, is that your force distribution might not be even through all the sections. All right, so let's take this to Excel and do it up. Alright, hell yeah. So this is just a test with the Yeti microphone. Make sure it's not too loud. And booyah. And so here we go. Here's our equation, natural log, and I think I'm done, so we're just going to go